Yes. On YouTube. Okay. Yes, that's quite all right.
So you want me to point on the computer, right?
You can do. A lot of people have been using this, which obviously the YouTube people can't see.
Okay.
Just click that onto your lanyard.
Yes. This way, yeah.
If the lights will stay down to the lights will
Hopefully. Still on setting at the moment. Would you like some help?
I think this this side.
Yes.
This way? Yep.
Yes, perfect. That should be. Is that? Can you speak into it? Is it working?
Yes, test.
Yeah, oh yes, yep. Perfect. Yeah. So a lot of people have been using this.
Oh, great. No, I prefer. No, I
can't see it, but I'm sure it should
it's
be fine
if
you use your words.
That's good. Thank you.
Which one's mine? Is it that one? This one? I'm going to step out for a minute so I can check the YouTube's working well.
All right.
But everything should be set up.
Okay. Oh, yeah. Nice setup.
Okay, so I think we can start the morning session. The first talk is by Daniel Pomaret, Discovery of Large-Scale Structure by the Cosmic Flow Program. Thank you, Daniel.
Thank you so much. So yes, I'm going to present multiple discoveries that we have made with the Cosmic Flows program. And these discoveries are synthesized for the most of them in this artist view. It's an artist view which is quite close to the reality that is disclosed by our reconstructions. So it's about the reconstruction of the Laniakea supercluster, to which our galaxy, the Milky Way, belongs. I will talk about also the discoveries of two so-called repellers, the dipole repeller and the cold spot repeller, which are presumably associated with giant voids. I will present the discovery of the south pole wall. And I will conclude mostly with the discovery of Oleilana, a shell-like structure that we have discovered in the distribution of the Cosmic Flows 4 galaxies. I will also briefly talk about our current work, which is about what the Cosmic Flows 4 catalog is telling us about the Sloan Great Wall. And I want to thank Alexia for organizing this conference. And for inviting me, and I wanted to show with this little logo here that thanks to you, the University of Lancashire is at the center of the universe today. So the story begins with, of course, Hubble, Emerson, and Sandage. So thanks to the data they could obtain at Mount Wilson and Mount Palomar, they established our vision of the universe, which is essentially isotropic and homogeneous, and which is described by the Hubble law, which states that the galaxies recede at a velocity that is proportional to their mutual distance. However, others, shortly after, were wondering if this Hubble law could be perturbed by gravitation. And by the way, galaxies are distributed on large scale. So of notable importance to me are the paper of this letter sent to Nature by George Gamow in 1946, where he was discussing the theory of a super galaxy, that is a galaxy of galaxies in rotation, and it was a very natural idea because planets are orbiting stars, stars are orbiting the center of a galaxy in spiral galaxies, and you could wonder if you could extrapolate to the next level by having galaxies rotating about a common center of gravity. From the, from the experimental point of view, we have a pioneering figure in Vera Rubin, who did her master thesis in 1950 on the anomaly of the distribution of velocities in a catalogue of 70 galaxies, which was for her the sign of the existence of a structure. So this work that she presented at the AAS meeting in Haverford in the winter of 1950 was very, very badly received for the most part by the community. We have to note that at the same time, my fellow countryman Gérard de Vaucouleurs was in Australia at that time, and he was studying the distribution of the galaxies using published data, and he said that it was, I read his memoirs, and he said that it was very difficult at that time to go against this vision of isotropy and homogeneity. And it's only because he read the abstract of Vera Rubin in this conference that he found the courage to publish this paper on the discovery of the local supercluster of galaxies. So that was in 1953. This is really the first large-scale structure that has been discovered by a Frenchman, of course. And this is, to be fair, this is not really new, because the astronomers of the 19th century, they all knew about this because they found this structure already in the distribution of the nebula. But of course, they did not know that they were galaxies, that they were extragalactic. So Vera Rubin, she, after this Master of Science thesis, she went to do her PhD with Georges Gamow, and she carried on studying the distribution of large-scale structure at this point. And then, very important for my talk, in 1966, she published with Ford the Rubin-Ford effect, which is the observation of a bulk flow in a very small sample of galaxies, 96 galaxies. They got this velocity of 400 kilometers per second, which is about right, but they didn't get the right direction. And this was very controversial. Vera Rubin got very upset about that, and she left the field. So she went to work on something else, and she discovered dark matter in the rotation of a spiral galaxy. But anyway, she can be considered as the mother of cosmic flow studies. She's really the first one. One very important occurrence was the discovery of the Great Attractor by a group that we called the Seven Samurai, which included people that were very close to Vera Rubin. For example, Sandra Faber was her postdoc. Donald Lynden-Bell was a very close friend of Vera Rubin. And they got this very important result obtained on a catalogue of 400 galaxies, where they studied the peculiar velocity of galaxies, a peculiar velocity being defined using the total velocities of galaxies being the sum of two components, the one from the expansion of the universe and the one which is everything else, most presumably acquired from the gravitational influence from everything that is around the galaxies. So it's these peculiar velocities can be considered as a perturbation to the Hubble law. And very importantly, we can measure only radial component of peculiar velocities, nothing else. So in this sample of 400 galaxies, they saw this flow. So you see when the markers were empty, it's like they are pointing toward us. They are inward, and when they are in black, they are pointing away. And they saw this flow, we call it a bulk flow, toward the region around the Centaurus cluster, 60 megaparsec away. So you see we were at 70 galaxies, 96 galaxies here. We moved to 400 galaxies. And then in my current project, we carry on this path in the context of our Cosmic Flows collaboration, which is a kind of an informal collaboration where we have a quite well-defined task. So we were 4 people working at the time of the discovery of Laniakea, with Helen and Brent working mostly on observations, Yehuda Hoffman working on the theory, and myself working on the visualization, or let's say the three-dimensional cartography of all the results that we obtained in this context. But of course, many more people are working with us, in particularly in this time, Noam Libeskin and Aurélien Valade. And we have a strong connection with the CLUES Constrained Local Universe Simulation collaboration. So my work is to do three-dimensional visualization. So I use a software that I've developed myself since 2005. So I have been working on it for more than 20 years now. I am probably the last of the Mohicans, still working in IDL. And you too? You're working in IDL, so we can be friends. It reached now 120,000 lines of code of IDL. And you can do such thing as looking at an histogram of a density field. You click on it, and you will get the surface that are at this level of density in the universe. And you can, so in this way, visualize the cosmic web, let's say. Our first work together with this group was to analyze the cosmic flows 1 galaxy. So you remember the 7 samurais, they were working with 400 galaxies. Thanks to the work of Helen and Brent, we got the publication of the Cosmic Flows 1 galaxies, Cosmic Flows 1 catalog of 1,700 galaxies. And we published a paper in the Astronomical Journal where we published the cartography, we call it the cosmography, of the local universe using this catalog. And this was published and it made the cover of Astronomical Journal at that time. So here is the reference. And it's typically the kind of products on which that I am producing. So this one is very complex. I won't show any more stuff that is as complex before. But it captures many things that we do. So you have these arrows in blue. These are the measurements of the peculiar velocities that are inward. So they are coming toward us. In red, they are pointing away from us. So they are outward peculiar velocities. All these white lines are streamlines of the reconstructed velocity fields. So they are a very basic way to visualize a velocity field. And the colored image that is in the background is a reconstruction, it's a slice of the reconstructed density field. And on top of that, we have put galaxies from another catalog, from an ancillary catalog, a large catalog of redshifts of galaxies. So we can compare things that are independent. So what we see here that we have this phenomenon, we visualize this phenomenon of evacuation from the local void. The local void that was discovered in the 80s by Brent Tully is confirmed here as an inner dense region of the universe from which the flow escapes because it is underdense, it is less dense than the average density of the universe. And in doing so, the flows are following complex routes that follow the filaments of the cosmic web. And if we do a view that is orthogonal, in this previous view, the Milky Way was here. And by the way, I am working in the supergalactic coordinate system with the y-axis here and the z-axis here. And we have this kind of bias that we always work in kilometers per second as a unit for positions, for the distances, because it's related to this question of the Hubble constant. If you want to have it in megaparsec, you can divide by your favored value of the Hubble constant, be it 75 or 67. And in my plots, I always bring back the dimension of the view that we are having here in both kilometers per second, megaparsec, and million light years, so that you can choose. So this is an orthogonal view where the Milky Way is here. We have the Virgo cluster, and we can see the phenomenon of the great attractor that was discovered by the 7 samurai with a major effect of a convergence of the flow onto this region which is around the Centaurus cluster. And you can see here that we don't go much beyond the great attractor. So thanks to the publication of Cosmic Flows 2, we went much further away. So here on the left, you have the Cosmic Flows 1 galaxies. It stops very, very nearby, while here we go much beyond the great attractor, the Centaurus cluster. We go as far as the Shapley supercluster, which was co-discovered by Scaramella, of whom we spoke yesterday. So you see that the coverage is much deeper. We go up, here you see in black galaxies from a large catalog of redshift survey. You have the Great Wall here. Here you have the Perseus Pisces filament. Here you have the norma Pavot-induced filament, and we cover all this in Cosmic Flows 2. And what I wanted to show here is, yes, you can see in this slide that you have data, you have regions where we have no data. So this comes from the fact that there is this famous zone of avoidance, the zone of galactic obscuration. So for an observer, the sky is divided in two. You have the north side of the galaxy and the south side of the galaxy. And along the equator, you cannot see what is hidden behind our own galaxy, which is made of 100 billions of stars, molecular clouds, and a lot of dust. So this is an observational difficulty. Yes?
So here, as you said before, here you have a radial structure.
Yes.
But in the previous plot, which is very nice,
Yes?
that doesn't look at all red.
Yes, because it's...
How do you reconstruct?
Yeah, it's a three-dimensional reconstruction, and this is the task of Yehuda, which is using a Wiener filter approach, a Wiener filtering of the peculiar velocities. And it gives us the most probable model of the three-dimensional velocity fields, taking into account the data, the error on the data, and the parameters of the standard model of cosmology. So it's
assuming that it is curl-free. That's important.
sorry?
It's assuming that it is curl-free. There is no curl in the velocity.
No what? No.
It's just a
Okay.
rotation.
Okay. And so, so indeed, so we don't have data indeed in the zone of obscuration. And despite this, we are able to reconstruct the field, either the velocity field and the density field, in the obscured region. Because if you have galaxies which are hidden behind, I mean, if you have a structure which is hidden behind the zone of obscuration, it will influence the galaxies that are in our sample, which are located on both sides. So you can feel the gravitational influence, and you can get a full sky reconstruction of the local universe. So that's what happened when we looked at the reconstruction of Cosmic Flows 2. We discovered this structure, which is a region of the local universe inside which the flows, which are represented here by streamlines, are converging on a single attractor, which is the great attractor of the Seven Samurai. And outside of this region, outside of this frontier, we see neighboring attractors, which are completely separated from our own volume, inside which the streamlines converge. So when Brent saw this map, he realized that we discovered a structure which he has never seen before, that we call a basin of attraction. And since you know, in the history of this field, there was the notion of supercluster of galaxies. It's a vague notion. It has never been defined in a mathematical way. So we proposed this notion of this concept of basin of attraction as a way to define a supercluster mathematically. And that was the subject of a paper that we published, that was published by Nature. And you see the beauty of using peculiar velocities is that you reconstruct really a completely three-dimensional structure that goes full sky. So if you look at it as a three-dimensional surface, this is the surface of Laniakea, inside which the flow converge. So this structure is closed in all directions. It contains what was historically designed as the Virgo supercluster, that is the local supercluster of Jar de Vaucouleurs. It contains also the Hydra Centaurus supercluster and the Norma Pavot-induced supercluster. It's a kind of supercluster of supercluster. So our galaxy, the Milky Way, belongs to this structure. It's located here at the origin of this coordinate system. And it happens that we are in a very non-important area of the local universe in terms of density. We are in a quite relatively underdense region located in the remote periphery of the structure, close to the border with the Perseus Pisces supercluster. So we had to give a name. We wanted to give a particular name to this structure. So you know, in Hawaii there is a kind of sociological problem. I mean, a cultural problem with the people that are of Hawaiian origins, because some people in this community feel that their culture is not respected, and in particular for what concerns the Mauna Kea Observatory and the other observatories, because they are built on mountains, on volcanoes that are sacred to their beliefs, and they are fighting against future developments of astronomy at Mauna Kea. So they have been protesting, they have been blocking the roads to the observatory, and more importantly, they have been they have been going to the court to stop the development of Mauna Kea, and in particular the construction of the TMT, the 30-meter telescope. So in the spirit of talking to this community, there have been several contacts where we try to involve like teenagers or kids and ask them to propose names for astrophysical discoveries. And it became an official business of the University of Hawaii. But here, Brent decided to go private on this initiative, and we contacted Professor David Nawa Napoleon, which was professor and chair of the Language, Linguistics and Literature Department at the Kapiolani Community College, which is the biggest university in Hawaii. So he proposed the name Laniakea, which comes from the contraction of two terms, Lani, which means the sky, the heaven, and Akea, which means huge, broad, wide, spacious, even immeasurable, and that gives us the name of Laniakea. Then, carrying on with the analysis of cosmic flows 2, we discovered the dipole repeller. So it happened when we visualized the structure of the full velocity field, and where we saw a pattern of attraction and repulsion. So here it's a huge map. It covers 1.7 billion light years around the edge of the cube. We see here in red and gray surfaces and filaments, surfaces of the knots and the filaments of what we call the V-web. The V-web being obtained by the analysis of the shear tensor. So this shows you where the flow is collapsing on three orthogonal directions where it is in red, and two orthogonal directions where it is in gray, which is a signature for a filament. So this just serves to guide the eyes. Let's say you can recognize the Shapley, the Hercules supercluster, and the great attractor, the great wall with comma here. So the velocity field exhibits a pattern of both attraction but also a repulsion. There is a point where there is a repulsion, there is a point where the flow is diverging. So what about it? Yehuda had the idea of reverting the gravitation. So here on the left we visualize the velocity field. And here on the right, we visualize the velocity field multiplied by -1, which has the effect of reverting the velocity vectors. And there you can see that instead of a divergence here, you see a convergence of what we call the anti-flow. So you can pinpoint precisely a region. And we call this place a repeller, because it's a place that is presumably, well, it repels, because it's presumably underdense. So matter escapes from this place on its way to regions that are more dense. Another point that we observed is that this repeller is located precisely, anti-aligned with the dipole of the CMB, which is related to our velocity in the universe. The motion of the local group in the universe. So the dipole repeller is precisely located in the opposite direction of the dipole of the CMB. So we got published for this paper in Nature Astronomy when this new journal was created back in 2017. So we were in the first issue. Here you have the dipole repeller, the Shapley attractor, and here for comparison I have put the surface of Laniakea here, which is about 500 million light years. So we analyzed the properties of this field, this velocity field, and we found that it exerts a push on the local group of galaxies, which is about 10% of the total motion, so about 60 kilometers per second, which is roughly comparable in strength to the pull that is exerted by the Shapley attractor. So by analogy with the basin of attraction, we propose this concept of basin of repulsion, which can be visualized using the anti-flow. And you can, in this way, define a basin of repulsion around this repeller. So being located at the extremity of the data coverage, we are not sure that we can capture the entirety of this basin of repulsion. And now, if you want to make a measurement of the size of something of a large-scale structure, but on the void side, on the underdense side of the universe, you can quote a radius of 1.3 billion light years, and you can presumably assume that it is twice as large, so a diameter of typically 2.6 billion light years for this entity. Presumably it is associated with a void, and it is difficult to chart as it is located in the vicinity of the zone of avoidance. So this is really the beauty of this technique of studying peculiar velocities. They give you information on what is hidden in the zone of avoidance. So then in 2016, we moved to the Cosmic Free catalog. So here you have the evolution: Cosmic Flows 1, 1,700 galaxies; Cosmic Flows 2, 8,000 galaxies; Cosmic Flows 3, 18,000 galaxies, with a huge addition in the celestial south. So thanks to this addition, we made another discovery of another repeller, the cold spot repeller. So we both confirmed the dipole repeller, and we found another repeller. Here I was visualizing the flow, here the anti-flow, so we can pinpoint the location of this repeller. And we called it the cold spot repeller because it can be speculated that it cold be associated with the CMB cold spot, which is a particularly cold and extended region of the CMB, which was discovered in 2004 in the WMAP data. So this cold spot is both very large and very cold, and it has been speculated that it could be it could find its origin in the presence of intervening giant voids, which could be located, let's say, in the region of Eridanus. So there was, for example, this paper by Andras Kovacs, which should be here. Andras, nice to meet you, Andras. I didn't know you. I saw that you were on the conference. And Juan Garcia Belidos. Andras is working. Maybe you are going to talk about it today? Yes, great, that's great. So you have mentioned that it could be due to either a giant void, a super void, or an alignment of smaller voids. So it's a very interesting topic, and our observation goes in the right way in this interpretation. So we made another discovery thanks to Cosmic Flow 3. We discovered a huge galactic filament, 1.4 billion light years long. So on this map, this is an 8-off projection that I have centered on the celestial South Pole. The North Pole here, with the North Star, let's say, is located here on both sides. But here we are interested on what is going on at the South Pole. So here, for reference, you have the Shapley supercluster. Here you have the dust of the Milky Way. And we found these filaments, which was never observed before, which is located in this region here, so very close to the zone of galactic obscuration, And also here you can recognize the large Magellanic Cloud, the small Magellanic Cloud. And here we have this stuff that we call the chameleon cloud complex. So it's a region that is very busy in our galaxy. You have these large molecular clouds which are hiding what is behind. So that's where we find this, the heart of the South Pole Wall is located behind this chameleon cloud. So it's probably why it was never observed before. Here you have the visualization of the density field in gray, anisosurface and the density field. And here you have a visualization of the streamlines, and it shows that there is a flow with a frontier here between something related to the Perseus-Pisces supercluster and here something that is related to this structure of the South Pole Wall and ultimately converging onto Shapley. Here you have the attractor, the great attractor. So we have several structures appearing like this in Cosmic Flow 3. Here I superimposed galaxies from a large redshift catalogs, and we can see that indeed there is an hint for something also in the distribution of galaxies, but it was not noted before. So here it's a comparison with the Sloan Great Wall. So the Sloan Great Wall is 1.4 billion light years. The South Pole Wall is has exactly the same size, but it's located at half the distance. So it's really quite amazing that such a huge structure was never noted before. But then again, it's thanks to the peculiar velocities that gave us this information. So I come now to the publication of Cosmic Flows 4 in 2002. Now we have 56,000 galaxies that comes from 8 methods, and in particular, a lot of data came from this catalog, the SDSS peculiar velocities, and this time we got a lot of data, new data, this time at the North Galactic pole, the North Galactic region. Here on these basic views, you can recognize the Sloan Great Wall here. Here on the orthogonal view, the Sloan Great Wall is here. And you can compare with stuff that we have already talked about, like the CFA Great Wall here. So now my talk is going to look a bit like your talk yesterday, Alexia, because what happened when Brent made some basic plots for this paper, he made a slice, and he found something that looked like a ring. So it can be difficult to convince yourself, but Brent saw it immediately. Here, to guide your eyes, we have put a ring of 1 billion light year diameter. And the fact that we're talking about 1 billion light years, it rings a bell. It could be suggestive of a structure of the BAO, the baryon acoustic oscillation. This is the diameter you expect for BAOs at the present epoch. So we conducted a very deep statistical study of the Cosmic Flows 4 sample, and more precisely the SDSS sample. That's really where this ring is located. And we realized, but it was also thanks to the visualization, that we could extrapolate this ring to a shell. So actually, Brent asked me first of a shell, but first in the paper we presented first the statistical analysis, and in particular the fit of the data, which gave us the center and the radius of this structure, and a very significant result when we fit the data with a BAO model. So the radius that we find is about 500 million light years, and here on this plot, it is with the knowledge of this fit that I have colored in red the galaxies that belong to the shell of this structure. So now, what I show you now benefits from the knowledge of this fit, right? So we know the center and we know the radius. So that's how we color here in red the galaxies that belong to this structure. So here you have 5 colors for the galaxies of cosmic flows 4. So they are in red if they belong to the spherical shell. They are in black if they belong to a central overdensity, which is associated with a supercluster, a well-known supercluster, the Bootes supercluster, where there are something like a dozen of galaxy clusters. And in gray, otherwise. And here also in this plot you have these big circles, so they are associated to galaxy cluster of the Abel catalog. And they have been associated to some supercluster in a paper by Enasto and his co-authors back in 2001. So in this view, we can see that many structures belong to this ring. You have the Corona Borealis supercluster, you have the Ursa Major supercluster, you have a great deal of the Sloan Great Wall, and you have other superclusters that were identified by Enasto and co-authors.
Can I ask something? I'm a bit confused.
Yes?
We call it a BAO shell because there is no center to a BAO shell. Every point is the center. So there should be a shell around every point in the universe, not at a particular point.
Well, if I understand correctly the physics of the primordial universe, there are overdense patch,
Correct, that's correct.
and from there you have a spherical shell starts from every.
But there is no specific center.
No specific center. Ah.
Because every point in the universe has a BAO shell around it, not a particular point.
It's an average. It's an average cost.
It's a statistical.
Well, it's like a background. They create a kind of background because they were generated from all the points. But here we think that we found an individual one. Yeah.
I'm not questioning
Yeah.
what you see
Yeah.
on the sky. All I'm
Yeah.
saying is that in interpreting it as a BAO shell, I'm
Yeah.
confused by the fact that this has a well-determined center, as you pointed out.
Okay.
And in the cosmological context, I would not expect any structure to have a well-defined center, because every point in the universe is the center
Okay.
in our current understanding.
You could imagine that somehow there is a big peak somewhere, and that generates a particular strong.
Yeah.
But it would not be the standard BAO shell, is what I'm saying.
Yes. Yes. Oh, I have to rush. So I'm going to make now a 90-degree rotation. So we are going to have another point of view of the structure. So it's an orthogonal view. So we see that the front face, so we are located here at the origin, and the front face of the shell contains, it's quite amazing, the Great Wall with the Leo supercluster, the Coma cluster, and the Hercules supercluster. So it's quite amazing when we saw this for the first time. And also that this is quite amazing, in the cavity of the shell, we find the Bootes void, which is historically the first great void that was discovered by Kirchner and co-authors. So we published this. It's quite so it's really speculative, but we put a question mark, right? But if it was true, this was really amazing, because it would be 53 years after the prediction by Peebles and Yu in Princeton and by Sonyaev and Zeldovich in Moscow of the BAO phenomenon. So this paper is mostly about the statistical analysis and also of the data, and using also a set of mock galaxy catalog to see if we could create such a structure by random chance, by random alignment. And we find that on 256 mocks where we have suppressed the BAO, we find only 2 examples where we can reconstruct such a shell with the same level of significances, but they have completely different radius. One is much bigger and one is much lower. What's amazing also is that Ole Ilana provides the new measurements of the Hubble constant, which is quite high, and which contributes to exacerbate the so-called Hubble tension. So what about his name? So here again, we wanted to give an Hawaiian name, and Brent had this idea to call it Pele's Lay. So you know, a lei in the Hawaiian culture is a crown of flowers. And in the religion, in the religious belief of the Hawaiian people, the archipel of Hawaii was created by the goddess Pele. She's the mother of the islands, of the volcano. She is also the goddess of the fire and of violence. And Brent, this time, he consulted experts, and they said, no, you cannot do this. She's too much of a sacred figure. It would not be accepted by the Hawaiian people to use her name. So we asked to Caillou and Larry Kimura at the University of Hawaii at Hilo, which are leading a group which is officially in charge of finding names for the new discoveries, involving teenagers and kids of the schools in poor areas of the big island of Hawaii. And for example, it's them who came up with the name Oumuamua for this very famous interstellar asteroid which visited the solar system a few years ago, and many objects. So they proposed this name, Oleilana, which is a brand new name. It has never been used before. You could type it on Google before we published the paper. It didn't exist on Google. And it is inspired by a sentence of the Kumulipo, which is the Hawaiian creation chant. So this is a chant of 2,100 lines, such as this. And it tells you the creation of the universe, how the universe was created. And at line 124, you find this sentence, Oleilei kalana akapululi, which means from deep darkness came murmurs of awakening. So which is really fitting for the Beao phenomenon, because something was vibrating in the dark and was making a sound of something that was waking up. And since this would have been too long for a name, so it was contracted in this new name, which has never been used before, Oleilana. So this is an artist's view, which is very close to the reality as they appear in our reconstruction. So, but we have enhanced the visualization of Oleilana. So you have it summarizes all the discoveries I told you about with Laniakea, the cold spot repeller, the dipole repeller, the South Pole wall, and Oleilana. And now we are working on reconstructions, because what's amazing is that Oleilana was discovered without any reconstruction. It's only looking at the distribution of galaxies. We didn't use the peculiar velocities of galaxies. So we didn't use any reconstruction of the velocity field. So we have been working on it using a new theoretical framework based on an Hamiltonian Monte Carlo method, where typically we use realization of the velocity field. So we use typically we compute 1,000 realizations that are each compatible and are each as probable, have the same level of probability, and you can either consider at the end a mean field, or you can do statistical studies by studying how things vary from one realization to the next. So here is the mean density field with the South Pole wall here, the Hercules supercluster, Shapley. So we are in known territory. And here, everything that stands out is the Sloan Great Wall. Sloan Great Wall is so strong that we see it in 100% of the realizations. You can see it here in a single realization. You see, this is very noisy. And here, of course, when we take the mean, it becomes all very smooth. So the Sloan Great Wall is really the thing that stands out in Cosmic Flows 4. So we published this reconstruction in Nature Astronomy about 2 years ago. And we did the cover of Nature Astronomy. Here it's quite amazing, this picture. This is the full flow of Cosmic Flows 4 in terms of its average. And you can see something, a huge phenomenon, what we call a bulk flow, which goes all across the map. So, and which is like, you have more than 1 billion light years from this point to this point. And the attractor is really located at the border of the data. And we can suspect that we have something really, really huge, that it's something so huge that maybe we will never reach it in our lifetime in terms of data, in terms of peculiar velocities.
Where is Shapley in that picture?
Shapley, it's here, this attractor, yeah.
And where are we located?
So I didn't point, it's here. Yeah. You can see I know very well, you have a divergence here between stuff that goes to Laniakea and to Shapley, and stuff that goes to Perseus Pisces here. So we had now a statistical approach of the basins of attraction. We call them the probabilistic basins of attraction. So for this 1,000 realization, you can fire streamlines and look where they end. And you can identify this way attractors. And you can build the probability that each point in the universe can belong to these various attractors. That's how we have a new vision of the Laniakea basin of attraction. We have a probabilistic basin of attraction around Laniakea. And this one that stands out is the Sloan Great Wall. So I'm nearly finished. This is what we are doing now. And I have to tell you now that so we are among friends now, right? So I can say something quite private. We have published this result on the Sloan Great Wall Basin of Attraction like 1 year ago to the Astrophysical Journal. And it has been blocked by the referees. So we have 2 referee reports who are telling us that this is not interesting, and they advise us to work on something else. So and that's it, and we are completely blocked. So I have presented this result at the Cosmic Flows conference last year, and this is really sad. We don't know what to do. So we reconstruct the basin of attraction of the Sloan Great Wall for the first time. It has never been done before. I mean, it's really something in terms of history. When the Sloan Great Wall was discovered, when was it? In 2005, it was the largest structure of the universe. It was quite polemical, of course. There were some colleagues who said it could be a chance alignment of smaller structure. And for the first time, we have a new vision coming from the cosmic flows, and which tells us that no, it's indeed, it's a singular entity. It's a big, single giant entity of as large as 1.7 billion light years, and it might be bigger because it's close to the limit of our data sample. So here you have this is what we put in this paper. We have maps of the convergence of the flows, the contents in terms of galaxy superclusters. The Sloan Great Wall contains many galaxy superclusters. And in passing, we also identify a huge void which is in front, in the foreground of the Sloan Great Wall, that we call the Sloan Great Void, and which is related. You know, when you look at maps of the void, it's actually the counterpart of the cosmic web. You have a web of voids. So you have voids that are interconnected, and we see the connection here with the Bootes void. So in terms of perspective, 1 year ago we have a meeting in Australia. So that was fantastic. We didn't have a Cosmic Flows meeting since before the COVID. The last meeting was in February 2020 in Cape Town. So we did not meet each other for 5 years. So it was the occasion to sum up the forthcoming project on peculiar velocities. So now the big player now in the field is DESI, with a lot of peculiar velocities that are coming from DESI. So there are already 10,000 peculiar velocities that were obtained by Tully-Fisher relationship in the DR1 in data release 1 of DESI. We have 100,000 galaxies coming from the fundamental plane technique. This has been already published. So this is in the north. In the south, we expect a huge amount of data from the 4HS project on the 4-meter Vista telescope in the Atacama. And we will have a lot of data soon from the SKA precursor ASCAP and Wallaby. And of course, there are multiple supernova programs that will feed us with long distance with peculiar velocities at long distance. So we expect 600,000 new measurements of galaxy peculiar velocities by the end of the decade. That's 10 times more than Cosmic Flow 4. So this is really what we said as a conclusion to this conference. So this is my last slide. I'm going to recap the sizes of these 6 large-scale structures I've told you about. So recall that BOR means a basin of repulsion and BO has a basin of attractions. So we have the Laniakea BOR is 500 million light years diameter. The dipole repeller, you remember I quoted 1.3 billion light years in radius, but you can reasonably assume something twice as large in diameter, so that's 2.6 billion light years. Cold spot repeller is even larger, 3 billion light years in diameter. The soft pole wall is 1.4 billion light years in length. Oleilana, of course, is 1 billion light years in diameter. And we have this paper now, which is submitted on the Sloan basin of attraction, which is 1.7 billion light years. That's it. Thank you.
Thank you very much, Daniel. And other questions, Marco?
Right, so very, very interesting to me. One clarification, when you reconstruct the density field, that's the Goldman matter.
Yeah, oh yes.
What happened?
I didn't say it, but of course it's a,
You reconstruct the
yeah.
density field
Yeah.
through the motion.
yeah, total matter, dark plus luminous.
Have you ever tried then to map not the velocity field, I love your straight lines, but the momentum field?
No, that doesn't ring a bell. No, I've never seen anything.
Discuss
Yes,
that
yeah.
later. You
Yeah.
will see why I asked this question.
Okay. Yes.
In that plot, the cold spot repeller, the velocity deconstruction seems to show infall onto Shapley from the far side. I know it's a theoretical deconstruction, not a direct measurement, but I thought in your latest Cosmic Flows 4 analysis by Watkins et al. 2024, you show the bulk flow continuing to rise beyond Shapley, not falling off.
Yes.
How
Yeah.
do I make these two things consistent in my mind?
Yes. No, I don't know what to answer. Yeah, there is something very fascinating in this bulk flows paper, and yeah, there's a show stuff that goes beyond, indeed, but no, I don't know.
I'm aware of specific data from the nearby supernova factory, who's tested to see if there was an infall onto Shapley from the far side,
Yes.
and there isn't. It's rejected at some low probability. But if it is due to something pulling us, that object would already need to have a mass of 10 to the 17 solar masses at that distance.
Yes.
This is 200 megaparsecs or so, right? I mean, it's quite far.
Yes. Yeah.
And even if I allow for the fact that all your distance estimates might be uncertain by, what, 15-20%,
Mm-hmm.
this is all fundamental plane.
Yes.
Even then, it's kind of a challenge to think of. I mean, you don't see any galaxies, so it would have to be a big lump of dark matter or something.
Okay.
I have just a question. What is the impact of the errors on the measurement of peculiar velocity on these maps? Have you
So that would be a question for Yehuda, but it's mostly Bayesian analysis. So we obtain the most probable field, right? So it's it's convolving many errors, many data, many errors. So yeah, that would be a question for Yehuda. Yeah.
Okay. Other questions? If not, we thank this.
There was one last. Sorry.
So just a second question, if you try to correlate what you see with other observable, like for instance Sunay Zeldavich?
No, I don't know if we have done that. No, doesn't ring a bell. I know. Okay.
Beautiful pictures, by the way.
Thanks. That's my job. So I can pass a message to the conference. If you have some need for a three-dimensional visualization, I would be very happy to collaborate with anybody on new projects. So don't hesitate. Alexia, if you want to visualize a giant structure in 3D, don't hesitate to. We are not competitors. Huh? We are a community now. Yes.
Thank you very much.
Yes.
Okay, so we have a short break now. 10 minutes.
Thanks. A very nice setup, huh?
Yeah?
Yeah.
Very much interested. You didn't know about that? Did you know about that before?
I knew, but it's long time. I mean, I knew. I even have the original conference proceeding from that. No, even earlier, something very old. Yeah, with the great attract.
That was in Hawaii. It was organized by Brent.
In my PhD thesis, I have a line of a quote about the great attract. I don't remember who was, maybe it was Italy or somewhere else, but there was a conference in Rome, and someone, could be Italy or whatever, was riding on a taxi on a taxi in Rome, and the taxi driver, I think, asked the guy, "What are you working on?"
Yes.
And he said, "Oh, I'm working on something called the Great Attract." And the taxi driver replied, "Oh, like Sophia Loren." And so this is the quote in my PhD. So, but anyway, so you see, I think it will be powerful. So, I would be interested in having your help in 3D plots, because you will see something part of my talk, because I work with a PhD student now. He's a Dr. Tourism. You're in Paris, not far from Tourism. And but he works with Gaia, so something mainly. But he was visiting me during the PhD, and we did this kind of different work. And this work is about extracting from embodied simulations a GR effect, general linear effect, okay? Using kind of post-Newtonian approach. So basically, I mean, you can see I did this also with full GR simulation, but it can be done even with just a Newtonian embodied simulation. You just need to interpret things. From the point of view of GR, Newtonian gravity is a ignored approximation. So you have to interpret things in that way. And then a certain technique, you can extract what is called the gravitomagnetic effect. And which is essentially the curl is generated by the curl of the momentum field. So that's why I asked about producing the momentum. Because you see, all of this is pure, nice, well done astronomy. But it would be nice, you would, with this, we would come up with a prediction. Because this effect is not measured.
I'm so sorry I didn't
But here, if you put reconstruct put together the density field, the velocity field, you reconstruct the momentum field. And then, computing the curl of this will give us a prediction of what we should see with this effect. And then, someone else should find an observable measuring, because this effect is not the same in GR of other modified gravity, so it would be a test of GR on cosmological scale. So anyway, it would be very interesting. Yeah, sorry. But we can talk more later. Sorry.
If that's the case, it's probably best to just gather on the phone. Sorry, he managed to get in.
Or you can have a super void. And you know what happened to the
So,
So is there anything I need to do to sign in? I just picked up the card on the desk.
could you just quickly grab me that A4 box there? Yes. I will need to just scribble your name on the visitor badge, but it's not. Are there any? No schedules here. Someone's pinched us. Okay, here we are. So we can officially go to break. be all good to go. Where's Edward?
Yes.
Can you just quickly click and click?
How this works?
Or your lanyard works fine as well.
Hello?
Oh,
Is working? Or not yet?
Yeah, it should be safe.
Should be. Try to
Hello?
work?
Hello? Hello? Hello?
Yeah, yeah,
Yeah.
I think so.
Okay.
And I will quickly nip out to check the thing.
Okay.
We need just a little minute on the yeah, I'll quickly check that it's all working on YouTube.
This is not working yet. I don't know if.
Sorry, that's. That should work.
Thank you. Wait, sorry.
Okay, so we can start the next talk by Edward Horrocks about localized detection of baryon acoustical resistance. 15 minutes plus 5.
Okay, thank you. Hello, everyone. I am Edward Horrocks. I am currently doing a PhD in Madrid, in Spain. These are some of my collaborators. And I will present today my work about the localized detection of BAO shells in DESI data. With a BAO shell, I want to say something similar to what Daniel showed us with the name Hoyleana. And basically, our current understanding of the BAO scale is mainly using two-point correlation function and non-localized technique to find in the redshift surveys, for example, the BAO scale. But for now, it's unclear if we can use an individual oscillation just placed in some region of the universe to measure the sun horizon in surveys. So the idea is constructing from Hoyleana, what is the first discovery of this kind. We want to check if we are able to find more than one detection, because right now Hoyleana is unique, it's just one. So of course someone can argue that it's maybe formed by chance, because galaxies are distributed in this way basically randomly. Or also maybe an issue that we want to solve, that is the Hoyleana is more or less of the same size of CF4 in the same order. So what we want to do now is find this kind of objects, more of them, to show if they are something physical or just made by chance, and also in larger volumes to have more statistics. And I think the DESI data are the perfect place to do it. Why we are interested in this kind of objects? My honest answer is because they are interesting. But I think mainly the main purpose is construct an alternative to the two-point correlation function to constrain cosmology, not only in a statistical way, without being blind basically to all cosmography and just taking the 2 point, but also take a look to one region of the universe and extract cosmology from that region in similar way as field inference, but with an astrophysical object what we can understand and also relate with the astrophysics and the properties of galaxies which are living in this region. So I think these are some reasons because this is interesting, and if you have some more ideas, I will be very happy to hear you in the coffee break. But before to start to looking for the rabbit, we want to understand how the rabbit is like. And this is a very nice plot from Einstein, in which I think is a very good, very nice idea what they had. They take point-like initial density perturbation, basically in an empty universe, you put only one point-like perturbation. In mathematics, it's basically Dirac delta. And they evolve this perturbation with all the equations what lambda CDM have in a linear regime to see how this kind of perturbation evolves in time. And you can see like the couplings between photons, gas, but basically I am very interested in this last plot because these are the redshifts in which I am able to detect this kind of density. And what I am learning from here is if I have a perturbation, it grows in a time, creating this kind of density, radial density profile, what I can divide in two different parts. I expect from this initial perturbation to have a high density region at the center and a little bump as a spherical shell in 3 dimensions in the galaxy, in the radial density or the galaxy distribution. So basically, this is what we expect to see. So my way to imagine the universe right now is something like that. If we see, if we take a look on only one of these guys, as I said, we can divide it in 2 parts. And to trace the first part, a good candidate is a cluster of galaxies because they are very dense, the most dense region of the cosmic web. And to trace the spherical shell, we can use just individual galaxies measured by their spectrum in, for example, DESI data. So we basically did a cross between 2 different catalogs. The first one contains just clusters detected using spectroscopic and photometric redshifts, and basically searching groups in them. This catalog was made 2 years ago and contains more than 1.5 million of clusters. And then we combine basically this cluster, the interesting region in which we have better measurements of individual galaxies in DR1 LRG sample. You can ask me why LRGs? Because bright galaxies are too close, so we are not able to resolve a spherical shell of this size, of the BAO size. And emission line galaxies are too far away, so we have too low density there. And LRGs are basically in the middle, so they live in the interesting region to do this kind of measurements. How we want to detect them? We used a method called wavelet analysis, what basically is a convolution of the field, density or galaxy distribution, to basically take, we take BAO shell type profile, like of this type, and we convolve this equation with the density field. So we are interested in this W, what is basically the value of the wavelet convolution. And the idea is simple, but as you can see, we can vary the radius and also the thickness of the shell. So basically, we want to explore the whole parameter space. And if we apply this convolution to the point-like perturbation in the initial density field I showed you before, we will obtain something like this kind of plot with a wiggle. The x-axis is basically the radius of the BAO, the y-axis is the thickness, and the wiggle basically shows the presence of an individual BAO, individual shell, in 3 dimensions, what disappears when we remove the baryonic acoustic oscillation from our cosmology. This is for now the prediction, the linear prediction for lambda CDM. And after presenting the methodology and the data,
does it actually have anything to do with lambda? This is baryons are there in any cosmology.
Yeah, of course, but
it's not a prediction of lambda CDM.
No, exactly. Yeah, it's a good point. It's not prediction of general lambda CDM. It's a prediction for one perturbation of lambda CDM. This is the...
Any cosmology with dark matter.
Exactly, exactly. So, first question, before to go for individual VAOs and this stuff, let's ask ourselves if we are able to detect just the spherical shell around the clusters we are selecting. Okay, this is the first step before to go to the individual objects. This is the same prediction I showed you before. And now we applied the idea of the convolution to simulations. This is a numerical simulation from a multi-target group. And basically, we take all the clusters we found in this simulation, and we stack the signal of the convolution, creating this plot. What's much more or less well away, and the prediction what we have from our individual perturbation in lambda CDM. And this is what we saw in observations. This is taking the clusters of our cluster catalog and using LRGs as a tracer of the three-dimensional shell. The good news is basically we recover the expected wiggle, and to quantify the significance of this wiggle, we basically select only one thickness value. And as you can see, the red line is here is the prediction for one perturbation in lambda CDM. This is the prediction from simulations, and this is what we obtain from observations. The green line here, the black line here, is for the universe without VAOs, the same as the green line here. Okay, this is a simulation without VAO wiggles. And here, the green line represents the same technique, the same idea, but instead of using clusters as a center, we used random position, basically. So what we are seeing here is basically a more than 5 sigma signal from the wavelet analysis in trying to detect the spherical shell, confirming that there is something significant around the clusters. Also, we can divide all the whole catalog between LRG1 and LRG2 in the same way as the DESI papers, basically dealing with different redshift bins. This is the number of centers I am using. I repeat, I am stacking all these centers for now, so I am not doing yet a localized search, but basically this is for just detect if the spherical shell can exist or not, okay? And as we can see in both catalogs, the signal is near to 5 sigma. So now we can do something very nice, what is we can take all the regions in which we have a positive value in the convolution and take a look for a first time to how an individual VAO looks like. This is, for example, the density, the number density distribution in the line of sight. And this is for a perpendicular view of the line of sight. And now I am showing you LRG1 and LRG2. We can see clearly the ring. Basically, this is a projection, of course. And also, for example, we can see that the perpendicular plot is have more anisotropy than the LRG1 because the observer is basically here, like in the y-axis. And also, my favorite detail of this plot is you can see this little line, what represents the redshift distortions of all the galaxies living around the clusters, what we are using. Just to show you how important is this finding, we can compare it with the previous attempts in SDSS made by Arnald Temur, in which they showed this, you can see it by eye more or less, and the spherical shell they found in SDSS now improves to a clear spherical shell in DESI data in form of this ring. So now, if we are able to detect the spherical shell, we can try to answer the second question. Can we detect an individual shell in one specific region, just one individual VAO? To do it, basically, we take all the regions in which we have the positive value in the convolution. We compare all these regions with the random distribution expected in that places. And we was seeing for more than 5 sigma signals peaks in the distribution. Oh, sorry. And this is the footprint of the sea. And every blue point is basically one individual BAO, what we found, of more than 5 sigma of significance. I am deleting them. I am removing all the duplicates, so these are unique structures. And as you can see, there are no visual biases made by observational issues or other different systematics. So we are happy to see them everywhere, basically. Everywhere when we was seeing. Also, now we can plot a lot of things. For example, this is the radial density, number density of all these BAOs. We can see, as we expect, the high density region at the center and the bump of the 3-dimensional shell in the expected place in which we want to see the sound horizon. Different colors here means basically different regions of the BAO to distinguish the perpendicular vision and the in the line of sight projection. So this is very promising because we are seeing directly the radial distribution of these objects. And for example, to compare with Hoeliana, what I think is interesting because it's the base of this research, we made the same technique for the place in which we expected to see the Hoeliana from the Daniels paper. And for now, I am using here as tracer not galaxies but clusters because the DESI galaxies, not all them lives in the region of the sky in which Hoeliana lives. But as you can see, just using clusters, we reach more or less 5 sigma in the Hoeliana detection, and this is the wavelet analysis, the convolution. So now, with our new friends in the sea, we can compare them with Hoeliana. And for example, I take it here the most significant individual BAO I found in LRG1 to just see how the signal is not only comparable but also higher, reaching more than 11 sigma in this case and in this other one. So, yeah, 5 minutes? Okay. Okay. Sorry. So basically, as I don't have too much time, I will show you the last point. After basically doing this analysis, now we applied the human eye to see if we check these regions, not only the statistics and this funny stuff, but the human eye to the distribution of points of galaxies, if we wanted to take a look if we see something or not. And basically, as this conference is about rings, here I'm presenting you another one of the density distribution in only one region. This is the difference right now. So you can see, for example, the BAO the most significant BAO in individual in LRG1, and this is for LRG2. And more or less, I think you agree with me if we can confirm that there is, by our human brain, something what we can detect. But of course, this is not the important issue what we want to handle. We want to confirm everything statistically with our methodology. So for now, I will finish my talk, giving you my conclusions. And yeah, that's it. Thank you very much for listening to me.
What H0 does that radius correspond to for you?
This is something very interesting to check. For now, this work is just about the detection. I am being blindly completely blindly to the cosmology and to the value of the, because I don't want to bias myself doing that. But in the next works, we will of course check what cosmology predicts these objects. And I think this is the most interesting part.
Have you tried to use the bright galaxy sample?
I tried, and I have uploaded in my presentation. Just to give you the idea, the issue in bright galaxies, I told you before, is basically that they are too close to resolve a large structure like a BAO. So what we found for bright galaxy samples, this is 1,000 of extra plots I have in my appendix. Oop. We found a wiggle, okay, but it's more or less of 3 sigma value. So it's interesting, of course, and with more data, we will be able to resolve more clearly the peak. But for now, we are focusing in the most promising region of the universe. Yeah.
Okay, thank you very much.
Thank you. Thank you.
We can go to the next speaker, Jim Hinkley, who is going to talk about tracing cosmic structure with neutral hydrogen after the
Thank you. Yeah.
Yes.
Cool. I'll put it on this side maybe. Oh. Alright. You've got the icon. You can use this to point and these to change. Brilliant, thanks very much. Thank you. Thanks. Hi, I'm Jamie. I'm a second year PhD student at the University of Manchester, working with Laura Watts, and so I'm going to be talking to you about work on simulating the transition from the end of the epoch ionization to the formation of late-time low-scale structure with neutral hydrogen, and looking at the phase transition kind of that happens there. So just first of all, I'm going to give a bit of background on this project, like why we started doing it, how we've gone through it, what instruments we're using. So start off looking at when. The time period we've been looking at, as I mentioned, was from the end of the epoch ionization to late time large scale structure, so about redshift 7 to 4. And I'm sure, like most people here, are familiar with the epoch ionization, but just to make sure we're all on the same page, the epoch ionization is where the universe goes from being essentially completely neutral as it's left after recombination to essentially completely ionized. And I've also highlighted it in this purple box here as well. So it's the last kind of like dregs, if you like, of neutral intergalactic medium that's left over at the end of epoch ionization, to where we have all of the hydrogen, or pretty much all of the hydrogen contained in dark matter halos. And the reason we've been focusing on this transition period specifically is because it offers insight into both the late-time cosmology, but also the astrophysics of reionization, whilst still observing at a lower redshift. And in terms of what we're going to use to observe this signal, the Square Kilometre Array is an upcoming radio telescope. It's going to be the largest radio telescope ever built when it's finished construction, and it's comprised of 2 different telescope arrays, one in South Africa, a mid-frequency array called SK Mid, and one in Australia called SK Low, and that's the one that we're going to focus on here in this analysis. SK Low observes between about redshift 27 down to redshift 3, and so it's going to cover that entire transition period that we're looking at. And indeed, there's a planned survey called the SK Low Deep Survey, described in the Red Book from 2020, that aims to observe over this transition period. in terms of how we're going to observe this transition, so I've mentioned neutral hydrogen before. So hydrogen is the most abundant element in our universe, a baryonic element, and it's hydrogen atom on its own undergoes a spin flip transition that's actually really forbidden. It, on average, only happens every 10 to the 7 years, but because we've got so much hydrogen in the universe, this actually ends up being quite a significant signal. It's something that we can detect. It's used a lot locally, so say, for example, at Jodrell Bank, some of the students use the little 7-metre telescope to look at the neutral hydrogen of the galaxies. Yeah, very detectable signal, but we're now wanting to extend that to beyond the local universe and out to higher redshift, and where we can use it for cosmological purposes. And we're going to use a technique called intensity mapping, which instead of resolving individual galaxies, it integrates the total emission from all of the galaxies within a single pixel of observation on the sky. So it means we can observe over much larger areas of the sky. And since cosmological structure lies on the larger scales, we can use it to, these types of surveys are really good to trace cosmology. And when we're observing using intensity mapping, in this work, we're looking for a signature of this transition in this 21 centimetre field that we detect. And we want to see if we can detect this transition, if we can detect a signature, what is the best way to observe it. So what kind of survey size do we need to use, what time, and how do we want to bin our observations in order to kind of pinpoint this transition. And the reason we're undertaking this project now is because the SK construction is progressing really well. We had first light last year. And we've got the prospect of observing not just the sky average power, like for example with the tentative edges detection at redshift, off the top of my head, I think 15. But also the power as a function of scale. Because we're using intensity mapping, I mentioned before, it's really good for large scales. It means we don't have to resolve individual galaxies, can carry out much larger surveys much faster. But the downside of it is we include everything in the observations. So we're going to get a lot of foregrounds, a lot of emission and contamination from synchrotron and free emission. And so a lot of, we're going to have to carry out a lot of analysis, a lot of cleaning on the data. And in order to extract meaningful constraints from the data that we get, we're going to need to build forecasts so that we can carry out data-driven analysis. And so the really accurate, fantastic hydrodynamical simulations such as TNG are great, but because they're so accurate, they take super long to run. And so with the amount of simulations we'll need to run to carry out data-driven analysis, these big super accurate simulations aren't super useful here. So instead, in this work, we've been focused on building a what's called a semi-numerical simulation, which combines almost like the best of both worlds. It's got it combines analytic relations with numerical techniques. And so I'm just going to talk you through now what we used to build a semi-numerical pipeline. So we've combined semi-numerical reionization simulation called 21 centimetre fast. It's public, it's well tested and widely used. And we've built from, we've taken the brightness temperature field from that, and we've built off of the density field that's been output. And we've taken the density field and we've identified where dark matter halos will lie on it by applying a halo finder. We built a watershed-based halo finder to work on a continuous or gridded density field rather than with individual particles. And we used something called the watershed algorithm. And here I've got a little schematic which just kind of gives you an idea of how the watershed algorithm works. So we took the negative of the density field and applied the watershed algorithm to that. And what you can kind of think of it as doing is filling up these basins from around the minimum of the potential, the gravitational potential. And once two regions overlap is where it segments, and it builds these, enables us to build these regions, these segments across a continuous field. Once we've found our halos, we assign neutral hydrogen to them using a deterministic neutral hydrogen to halo relation. We actually tested 3 here, but we found the best one to be one that's been fit to observational data up to redshift 5. And once we've assigned halos, we build a radial profile around it. We use a modified Navarro-Frank White profile. The reason we had to modify it is because Navarro-Frank White profile doesn't include effects of baryonic feedback because it describes a dark matter halo. But here we're looking to describe the neutral hydrogen distribution. And finally, once we've built our underlying late-time neutral hydrogen field, we now apply observational effects to the signal that we observe. So we apply the effects of instrumental noise. We simulate this as a function of scale by using the official SKA tools to generate the baseline distribution and calculate the instrumental noise off of that. And then also we simulate the effect of foreground avoidance by identifying the modes that are most affected by foreground contamination because, well, as we discuss later, foregrounds are smooth across frequency, so we expect them to lie on the smallest line of sight wave numbers, so the largest scales. So now I've talked a bit through the background, I'm now going to talk through the results, how we validated this pipeline, and what information we managed to get from this work. And just before I go into this section, I'm going to be talking about 3 different surveys that we've been looking at. So we defined a deep AA star survey. So AA star is the funded stage of SK low and SK mid. And it's going to have full operations. I'm also going to talk about a deep AA4 survey, which is almost kind of like a hopeful future extension to SK1 if the funding is required. And I'm also going to talk about a shallow AA star survey. So I talked about the deep survey, the 5,000 hour, it's 5,000 hour and 100 square degree survey described in the Red Book. We also look at a shallower observation, so we use 500 hours and the same 100 degree squared survey. So started off by looking at how the neutral hydrogen bias evolved. So we defined the neutral hydrogen bias as the square root of the ratio between the neutral hydrogen power spectrum and the underlying cosmological matter power spectrum. And in our simulations, we found that the bias became more linear with increasing scale or decreasing wave number, agreeing with previous literature, the theory. And we also, there are previous theoretical work on the linear bias, which is what we defined in this work as the mean of the scale, bias as a function of scale, up to the point where we see it becomes rapidly nonlinear with increasing wave number. And we got decent agreement with theoretical work, so that was a nice bit of validation for our pipeline. So once we'd validated bias, we next moved on to looking at a sky average value, which is the cosmological neutral hydrogen density, or the omega H1 parameter. and we looked at how that evolved as a function of redshift. So I actually show the outputs from 3 different runs of our pipeline. The red is the fiducial one that we ended up using, but we also show another observation-based neutral hydrogen to halo relation, and then a simulation-based one. And you can see here the one that we ended up using was the best fit to all of the data. And we can see it agrees, the evolution agrees nicely with observational constraints from, I think it's ionized carbon, C2, and with Lyman alpha constraints on the neutral hydrogen density out to redshift 3. So now we've looked at, we validated it against existing data, existing observational theoretical constraints. We next moved on to looking at the power of a function as a function of scale across redshift. And so we don't compare these to theoretical constraints. These are kind of like our own predictions now. So the main thing that happens over this transition is massive decrease in amplitude of the power spectrum, as you might expect, as the last of the neutral hydrogen is in the IgM is ionized. So you can see here that we're already at larger scales. We've got a power of about 10 to the 1. Just at 7.5 where this run started, that was at 10 to the 4, so, 10 to the 5, so it's already gone down by 10 to the 4 by redshift 6.7. We can see we've still got quite large neutral islands remaining. Even though most of the IgM has been ionized, we've still got this large island contributing to a lot of the power. So moving on to about redshift 6, even though we haven't got any large neutral islands, I've just realized we've not introduced this here. This is the cylindrical power spectrum. So this is just showing you the spherical, the power spectrum, but split into planar modes and line of sight modes. So when I talked about the foregrounds earlier and how they lie on the largest line of sight modes, they're going to be constrained to about here, and we'll talk about that later, but just realized I didn't introduce what on earth's going on here. So you can see by now the largest neutral islands have disappeared, but we do see lots of little neutral fragments remaining from the intergalactic medium that haven't been reionized, and we plot we split the contribution into the total neutral hydrogen power, so combining the late time contribution from the halos and the epoch of ionization contribution, and then in the green we also plot the epoch of ionization contribution alone, and we can see still at redshift 1 the epoch of ionization contribution, these little neutral fragments, even though they're so small, they still have sufficiently high temperature that they're dominating the power spectrum, even though they occupy such a small volume. But by the time we get to about redshift 5, we can see that the neutral, the late time contribution is starting to become significant. We see at the largest scales that the total neutral hydrogen power is starting to separate from the EOR only contribution. You can see we've got a couple islands remaining. But by the time we get to about redshift 4, that's when our larger scales are now directly tracing our cosmology. And apart from at the very smallest scales, which are buried under thermal noise, the neutral hydrogen power spectrum is a really nice tracer of the cosmological power spectrum and therefore of the cosmology. So you can see it's gone from being a really a potential constraint on the astrophysics of ionization to a nice constraint on the cosmology of this period. And so before we moved on to, I'll try that again. We wanted to look at the how the astrophysics, if we could detect the astrophysics of this region. So, because I'm a bit short on time, I'll skip over this because it's just a summary slide. We know that a delayed reionization is favoured by observational data. So we reduced the fraction of gas in stars, and we reduced the ionizing photon escape fraction. And we found that not only does it delay the timing of the transition period, it also causes almost a patchier, more drawn-out reionization scenario. And we expect from this work, we found that we can expect to see a significant difference between the two runs. So this is about a 10% decrease in the ionizing escape fraction and the percentage of the fraction of gas in stars. And we can see that this minimum here in the fiducial run in the grey is a lot less pronounced and also occurs about redshift 5 rather than about redshift 5.5 if we have a delayed reionization scenario. So this transition signal presents itself not only as a good tracer of the cosmology, but we can also use it to constrain the astrophysics of the epoch ionization. Finally, before we finish, just want to talk about how foreground avoidance affects our results. And we applied a horizon limit foreground avoidance scheme, which is kind of a minimal one, and essentially just cuts off any foregrounds that we expect, any scales that we expect to be most contaminated by foregrounds. And we can see that applying this regime at redshift 6.7, there's almost negligible of the change. We do lose information at the larger scales, but most is accessible against thermal noise anyway. And then by redshift 4.7, we can see that although they're buried in thermal noise, there's not a huge decrease in the signal-to-noise ratio by removing these modes. And again, it's just a question of losing the information at the largest scales. But most information is still accessible. And so with that, just to summarise, this transition signal, we expect it to be detectable with SK low, and we expect it to be able to be a good complementary constraint to UR power spectrum measurements on the astrophysics of ionization and potential contributor to cosmological constraints. And yeah, with that, just like to thank you all very much for listening. Thank you. Oh, yes, sorry.
So we had a very nice slide right at the beginning which showed how the universe has evolved through different stages. Are you able to give us just a very quick overview?
Yeah, of course. I'm going to I'll start with this one. Oh, sorry. Yeah, so this is going to be a real whistle-stop tour. Big Bang, big cosmic soup of like photons and electrons and protons. But the universe is expanding, and once we expand to a certain point, things cool down enough that they can form neutral atoms. So the universe goes from being big cosmic soup of protons and electrons and photons to the protons and electrons combining into neutral hydrogen and primarily neutral hydrogen, some helium and other things. And these photons free stream. But now, because everything's neutral and nothing's collapsed yet, we don't really have any light sources. So we enter the dark ages. And then we start to have, as things collapse more and more, we start to get the formation of stars and galaxies. And they emit ionizing photons that begin to reionize this ionized, then neutral, then now reionized universe. And then we get to late-time large-scale structure, where the universe is pretty much completely ionized, and most of the matter is contained in these large-scale structures, these galaxies and galaxy clusters. I hope.
Okay.
Yeah. Oh. Sorry.
So at this, I think after a few slides after this, you were saying the transition that you're looking at. Were you saying it's quite a rare transition? So what's the motivation of looking for this transition over
I think it's mostly that even though like it doesn't happen very often, it's just because hydrogen is so abundant that the signal it emits ends up being very detectable anyway. And yeah, because it's so abundant, it's a good tracer of the matter power spectrum. I can't say I'm super familiar with things like the helium, like using helium intensity mapping. But yeah, the hydrogen is a good tracer of the cosmology, and it's, I think, our only known probe of the Dark Ages, the cosmological Dark Ages that I talked about earlier. But yeah, thank you. Thanks very much.
Okay, thank you very much. So next speaker is Tobias Russell.
Oh,
He
you
will
don't
talk
want that.
about
I want that.
modeling the effects of parallel heterogeneity in
Can they just give him that?
for
Tell them how to put it on. Cool. Yeah, yeah. Hey, clip this onto your lanyard and stick this in your pocket. Probably put it higher up so it's close to your mouth. And then stick this in your pocket.
Thanks. Is that the click thing?
Yes. It'll definitely work. The sides should work and then the top should be the laser.
Yeah, that's good. Cool.
Thank you so much.
Right. Hi, so this is some of the work I've been doing in my project on modeling the effects of primary beam heterogeneity in SK mid for 21 centimeter cosmology. So, well, we've already been through a little bit about 21 centimeter cosmology with Jamie. I'll just do a sort of recap of what we do. So essentially in 21 centimeter intensity mapping, we use the neutral hydrogen signal to do cosmology, and in intensity mapping, we use arrays in single dish mode, meaning that instead of using them for interferometry, we use each dish individually. And in this case, we scan back and forth at constant elevation in the azimuth and build up these rising and setting scan patterns here. So that's how we build up our maps of data. And so the advantage of this is that we build up this large area coverage very fast, as opposed to your typical galaxy surveys, which is this serves as an alternative to. So typically with galaxy surveys, you need large numbers of resolved galaxies in order to build up your tracer of dark matter. However, here, because it's large areas much faster, we can use this as an alternative way of doing this. And while in galaxy surveys you have these nicely resolved individual points of galaxies, here we have a much lower spatial resolution, but as a contrast, we have a very high resolution in redshift and frequency. Okay. And as with all 21 centimeter cosmology, we have these very large foregrounds, mainly made up of synchrotron and free emission. And so one of the ways that we can remove these is by using principal component analysis, or PCA cleaning. And so essentially we do this by taking many maps across our frequency range, building a covariance matrix, and removing the first few principal components, which should, in theory, return to us our cleaned data signal containing the H1. And so what allows this to actually work is that foregrounds have this much larger relative amplitude and are highly correlated in frequency, meaning that in theory their information should be strongly concentrated in the first few eigenvalues of this matrix. So what you would do is you would compute these, compare their size, and this would generally give you an indication of the number of foreground modes you'd have to remove in order to effectively clean your data. However, when it comes to doing this in practice, we begin to see problems and complications in this stage of analysis, as well as other stages once we start considering a realistic beam. And this is partially where my motivation for doing this comes in that the beam structure will couple to this smoothness across frequency, the foreground, interfering with it and then causing complications for our ease of foreground cleaning and analysis. And so this is already an issue with one dish that we're looking into in intensity mapping. However, in the SKA mid, we are looking to combine data from two different kinds of dishes. And so in the two different configurations, AA4 and AA star, we're going to have the 64 existing meerkat dishes, which are 13.5 meters in diameter, and have this sort of construction, as you can see here. We're looking to combine them with either 133 in AA4 or 80 dishes in AA star. These SKA dishes, which are 15 meters wide. And so effectively, we have our sort of understood model of a primary beam, of the beam shape, sorry, which would just be, you'd expect to see, as I'll show in a minute, a nice main lobe and these side lobes that extend radially outwards. And typically, when you calculate your expected size of a beam, you expect it to easily sort of change linearly as we change wavelength or frequency, etc. However, in reality, we have these two quirks to the size and shape of the beam, which is an oscillating size across frequency, as well as an angular asymmetry. And these are caused essentially by the actual structure of the dish. So if we look at, just to compare how size affects on a basic level, we have what is our main lobe for SKA sized dishes and meerkat sized dishes. This is just a sort of simplified model to help give an overview. So our main lobe captures most of the signal, and then we have, as I say, these side lobes extending radially outwards. And so the best way to sort of generally understand the difference between an SKA sized dish and a meerkat sized dish is just to look here at like the overall strength of this first side lobe. It's the easiest way to see. You have these different power levels and different sizes from this. And so yes, in red here is just the equivalent Gaussian for the forward half maximum, whereas black is this sort of more realistic 1D profile of the side lobes. Okay, so that's a simplified picture. What does a realistic picture look like? So we have these measurements of the meerkat's beam as we move through frequency in the L band. And this is what I mean when I talk about the asymmetry of the beam, as well as this oscillating ripple in size. You can particularly see it if you look at the side lobes. And so in this work, we look at the Stokes I beam, primary beam, which is just the unpolarized model, as H1 is largely unpolarized. And in this, we can, to get a picture of what's going on, we should look at different beam models. And here's some commonly used beam models, as well as this IDOS model here. I'll start by saying the IDOS model is based on these measurements made directly of the meerkat beam. So we have this nice, more complicated, realistic model of the meerkat dishes because essentially they already exist and they are taking data. We don't have this for the SKA dishes just yet. But if we look at these differences between models, we see this realistic profile. The Gaussian, because it only has the main lobe, will capture this central main lobe fairly well. But because it doesn't capture any of the side lobes, if we want to get a more accurate picture, we have to look at something like a cosine model. And while this does look a lot better, obviously, than the Gaussian, you can see it begins to sort of fall out of step with our realistic measurements. And yet, if you want to look more specifically into this beam size oscillation effect, just in the context of meerkat, I recommend this work here. But to look into what I'm doing, these are the beam models I'm using. So I'm using a symmetric version of the IDOS model in that I've azimuthally averaged it. So you can see it, it's 1D profile here compared to others. I'm using a Gaussian model as a simplified example here, as well as a cosine model. So on here you can see the difference between a cosine for a meerkat-sized dish and an SKA-sized dish. So as I say, because we don't have these nice complicated measurements of the SKA-sized dish yet, in order to represent their beam, I use a cosine model. And so how do we start to look at how dish mixing works? I do this by taking a weighted average of the maps of smooth data created using my symmetric IDOS model for the meerkat dishes and the cosine model for these SKA dishes. So I take one map smoothed by one beam, one map smoothed by another, and I effectively do a weighted average of the two, and the weights I use here is simply the number of each dish type in these different configurations. So for the AA star case that I'll be showing in a moment, again, that's 80 dishes for the SKA and 64 for meerkat. And so this does assume that each dish is producing exactly the same map, but you can extend this logic to include more realistic stuff like the timestamps for each pointing in the observation as it's scanning. And so when you're doing this, you have effectively two options with your foregrounds. You either combine these smooth maps, inclusive of the smooth foregrounds, from all these different types of dishes together first, and then put it through PCA cleaning together, or you clean each kind of dish individually, and then combine their data afterwards. And so I'm effectively looking into the impact of doing both of these. How much of a difference does it make? How much flexibility do we have in how we can take and process our data? And so how do I do this? I test this on simulations of log normal H1 intensity maps. And I do this in the range of redshift and frequency that Meerkat is able to observe in, which is just, as you can see here, about 0.39 to 0.46. And as I said before, we have this very, very high frequency resolution. So you can see just in this small frequency range here, I have 246 maps, so that's a 0.2 megahertz resolution per each individual map. And I test this on a 500-degree sky patch centered on the South Pole, just to mimic what we'd effectively see when observing in the southern sky and attempting to avoid the problem of the galactic plane. And so the effective pipeline, is that we take our H1 signal, contaminate it with the corresponding foregrounds, smooth it with whichever beam model we're considering, and then take this smooth contaminated data, put it through PCA cleaning. We have our cleaned map here, and then we can take our clustering statistics from this. So in this case, I look at the angular power spectrum.
How do you get rid of the North Polar spur in the last picture?
How do I get rid of what, sorry?
From the middle to the last panel, you can
Yes.
see the North Polar spur is also gone with your PCA cleaning. That has a different spectrum.
Sorry, I'm not quite...
We will discuss this later.
Yeah, sorry, I couldn't quite understand, yeah. No worries, thank you. Okay, so effectively, how do we remove foregrounds? So as I said before, when you just plot out the basic size of them, you can see here there's a very drastic drop in size of the eigenvalues, so much so that you really can't see much of a difference between the different beam models. But if you look a little bit closer, you can begin to see, okay, there's this added complexity, so you can see them effectively crossing over each other, which gives us our first clue as to the fact that these different beam models very much do have an impact on how you remove your foregrounds. So as I say, huge drop-off in size. This gives us an indication, okay, we probably want to be looking at removing about 3 or 4 foreground modes. But because this doesn't tell us much on our own, ultimately, in order to get a better idea of this, we need to actually look at our clustering statistics or our clean data maps to find this. There is so much noise and quirks in the data that really it's hard to get a sort of theoretical overview without actually getting your hands dirty, so to speak. So if you were to look at a representation of the residuals of cleaned versus just smooth H1 data, you can see as you remove more and more foreground modes, just for a specific beam case here, we go from noisier data to data that's more centered around this 0 line. And if we move too far, you can see that these bins begin to drop into the negative, implying that we have now overcorrected and started sacrificing too much of our signal. And so moving back to comparing individual beams, what does this look like in data? So this here is just an individual L bin, if you will, covering the multipole from about 65 to 86. So this is just to illustrate that when you compare these different models, so Gaussian, our symmetric IDOS, SKA size cosine, and then this is our AA star combined case. You can see there is a difference, but it might be a little hard to see there. So what I've done here is effectively just replot this relative to what you get in the Gaussian case. So you can begin to see a bit of a better picture of how much an individual beam model will affect your data. So basically to illustrate the case that if you were assuming when you're cleaning and processing your data that, okay, the beam is represented by a Gaussian, you compare to this more realistic model of the IDOS Meerkat beam, right? You, in this specific frequency here, roughly around 980 megahertz, you might get 80% difference between what you think you're observing and what you're actually observing. So just to illustrate, again, you want to consider a more realistic beam with side lobes, and if you can do with something which captures this rippling size across frequency. And so moving back to combining dishes together and the impact of this, as you can see here, that looks identical, essentially, to the eye. So what's going on here is we found that there seems to be a very small difference between cleaning each dish type individually and then combining your data and looking at your power spectra versus combining all of your data together, both different dish types in one go, and putting this through PCA cleaning as one entity, if you will. And so if I just take one away from the other, you can get a little bit of a better picture of where you have these disagreements. And so on average, across this image, there's about a 1% difference between your data, and at max, there's about a 10% difference in different bins. And so the implications here is that it seems to be that you have this small difference would imply an amount of flexibility in how you actually process your data, which in the field of intensity mapping or H1 intensity mapping, where you have so much complexity from foregrounds, from RFI interference on site, from instrumental noise, and combining two different dishes together, the idea that you might have a fair amount of flexibility seems quite promising. So it would be good if we have this flexibility to process our data however we like in that sense. However, there are caveats to this. As I said, I'm using an SKA, for the SKA dishes, I am using a cosine beam model. And so for this, at the moment, because we don't have these nice detailed measurements of the beam, we don't have a representation of the beam ripple that we know will be present in these SKA dishes. So at the moment, it seems like we have this flexibility, but as I will say in my future work, one thing to do here would be to try and really zero in on whether adding in some kind of size ripple to this cosine beam will change this. Are we going to retain this seeming flexibility that we have when we go through PCA cleaning? It appears it handles this added complexity of two kinds of smoothing at once very well. Really zeroing in on whether this still remains the case, hopefully will give us a much better picture of how we go on to process all of the data that we take with the SK mid for the future of intensity mapping. I should also say, generally, to summarize again, when we do PCA cleaning, regardless if it's one dish or two dishes, bearing in mind how many foreground modes we remove, how much signal we sacrifice, it all affects your data to a large extent, obviously. And in addition to this sort of pending caveat of this size ripple and how much more it affects our data, when we have it in both beams, another thing to look at is adding even more complexity to foreground, so adding in, for instance, point sources, more instrumental noise, testing different patch locations and really pushing this apparent flexibility of PCA cleaning to its limit as we get closer and closer to the galactic plane, trying to expand the area of sky that we can actually use for intensity mapping. That's effectively really it for me, thanks. Yeah.
Okay.
Yes. Yeah.
So you kind of compare the individual treatment of each dish and then also of all of them together. But in this case, your model is actually identical for each dish. Well, in reality, the dishes, even the same design would have manufacturing differences.
Yeah. So, as you say, yeah, there can be pointing differences between that. With what I'm doing of this sort of seemingly simplistic weighted average between dishes, if we had measurements of each dish's beam, so the differences between it, we can to a certain extent gain an understanding of how they vary. It's going to be a very complicated picture, but I'll point out, this is one of my backups. So this is like, what's going on here is a realistic picture of the side lobes of actual measurements all the way out further, but what we are saying about different dish variation. So this is measurements, as I say, of the side lobes. If you look here, how they've built up this sort of average thing and this error, this is all different measurements of individual dishes. So you can see how much it might vary, yes. So if we have these measurements of each individual dish, you can extend the idea of doing a weighted average to this added level of detail of having, okay, of this, for instance, of the 64 meerkat dishes. If we have, if we have these different measurements, we can do a weighted average of what we expect the beam to look like for all of these. But there will still be complications from on the day how much is a specific antenna misbehaving in some extent. Do we have to flag it and remove it? Is there a particular issue, individually with noise on the day? But I guess to sort of loop back around, the point I'm trying to make is if we have all these different measurements of beams, you can very much extend this idea of doing a weighted average to model it further and just add in this extra complexity in that way. So provided you understand what the beam looks like from measurements, as you say, there will be differences. You can extend that and make predictions according to this.
In those cases, which way you think is better for the treatment of the data?
So as I say, there seems to be a small difference at the minute, but why I really drive home the point of in future work is looking at this artificial beam ripple is ultimately, we can't know what the SKA dishes look like until we get some astro-holographic measurements like we have for the meerkat dishes. And once we have this complete picture, we can do the most realistic modeling possible to actually get a better idea of what it will directly look like. But I think in order to just test something of comparable complexity, as I say, you should probably be able to take an artificial size ripple, superimpose this on top of how you expect your beam profile to change, and then compare existing meerkat models and this artificial SKA model and see if this small difference still persists. Because I would expect once you start adding in more and more complexity, eventually PCA cleaning's flexibility will break down. I expect it to become such that in the more realistic case, you will have to sort of process things on a more individual basis, then add them together. I would be quite skeptical if it remains super, super flexible as we add in more and more complexity. But at least for the minute, it seems to be much, much smaller differences between combining pre or post, combining together, cleaning as one versus cleaning individually, adding together. Compare that to, for instance, the differences between just maps made by one kind of beam to another kind. So compare a map used, or use a Gaussian profile versus a cosine profile. You look at the difference in data once you've gone through the pipeline of that, it's much, much bigger than if you were to just do this dish mixing in these two different ways I've gone over, sorry. Long explanation, but yeah.
Okay. Yeah. So we thank the speaker. We have to skip the coffee break because we are a bit...
We can have like 2 minutes, like 1 minute if you need to like stretch your legs or anything, and then we're going to go straight in at 20 past.
Okay.
Yeah. So like 1 minute if you need to.
Sorry about that.
But I'll get my next talk.
Thank you.
Thank you.
The light has its own life.
Oh, I know, doesn't it?
How does it work?
I have no idea.
You are the next speaker, right?
Yes.
So what's your name exactly?
Shirley.
Shirley.
Yeah.
That's the wrong top. That's not yet. There you are.
This one.
Yes. Let me just quickly get that up, and then
When are you going to launch the satellite?
Okay, that's okay.
Okay. It's not so far.
Yeah. We are actually on a quite tight schedule. So
that's that's ready for you now. You just need to clip this on and ideally clip this onto your lanyard.
Okay.
Because when you put it on your collar, it touches your throat. So just pop it on the lanyard here.
Here.
Yeah.
Okay.
Because if it gets too close to you...
It wasn't working very well, I think, with last speaker.
Oh, was it not?
Maybe
Can I check the big bit?
Hello? Hello?
Yeah.
Yeah,
Okay.
Maybe it's better to do it here, no?
A little bit higher, but if it goes too close to the throat, it vibrates on the throat and then it overdoes it.
Yeah.
My summary, I really would need the PDFs of the or some of them, or whatever you have. Can you send me a link?
So I have apart physics, I'm active in another field, which is education and research, policy of education and research.
Okay.
So I've been studying a lot the Chinese Academy of Science.
Oh, okay, great.
Maybe I have some questions I would like to ask you. Yeah.
So do you have some Chinese collaborators?
No, actually I don't. No.
Oh, okay.
But I once had some exchange of email with a Chinese lady who was the director of the evaluation program of the Chinese.
Okay.
I don't remember the name because it was a year ago or something like that. I was asking how they, because that's a very critical issue, for example, in Italy, how do you evaluate the research, results of somebody.
I see.
Now,
Yeah.
It's done with parameters, with publication, with numbers. Okay. Maybe if you have some ideas, we can discuss.
We can have some chat.
Because she told me, yes, we are going to publish it very soon, but she didn't. Okay, so.
We're just 2 minutes overrun, that's all.
I have lost my... Can we start? Okay. So, next speaker is Shui Chen, probing the primordial fluctuation with low frequency radio array on the lunar far side.
Okay, thank you. I'm really glad to be here, and I will talk about this, my recent work on this. So this is the outline of my talk. So I will first have some kind of general introduction, including the large radio array on the lunar far side. Then I will talk about the primordial fluctuations in the dark ages and probing them with the 21 centimeter arrays. So these are quantitative results are mostly based on two papers we in preparation. One is by my postdoc, Yuewei Wen, and one by my graduate student, Chen Zhang. Okay, so we have here, we have heard during this conference, people trying to use various means to probe the large-scale distribution. Now, if we look at the observable universe, basically we are limited by the particle horizon, which is kind of like basically around the cosmic microwave background glass scattering surface, as shown in this outer ring of this picture. But then afterwards, currently, we have a lot of very interesting measurements using the optical surveys, as you have seen, for example, in the talks by many speakers here. However, if we want to probe a large volume of the observable universe, potentially this 21 centimeter observations is giving you a lot of volume to probe, because after the Big Bang, the recombination, the hydrogen become neutral, and it can generate 21 centimeter emissions or absorptions. And even down to current universe, even though we have heard that there's reionization and the form changes from the overall distribution in the galactic medium to more tracing individual galaxies, but generally they are tracing the large-scale structures. So we, in principle, could, by observing this, probe very large scales. Now, we have a number of big telescopes, including the SKA, trying to map the sky. Trying to map the 21 centimeter emission, but if we to go to high redshift, then the problem is that the 21 centimeter line is redshifted to very low frequency. And for the very low frequency, if you want to observe from the ground, it's hampered by the ionosphere absorption and refraction, as well as by radio frequency interferences, which is very strong at the low frequencies. One potential idea is to build such a big array on the far side of the moon, where you are not affected by the ionosphere, and also the RFI from the Earth is shielded. This is the main theme of my talk. Oops, how do I move around? How do I shift the? Sorry.
What? Sorry.
How do I move to next slide?
Oh.
Okay.
Yeah.
Oh, okay. Oh, sorry. Okay.
No, it's because it wasn't clicked on.
Oh, okay. Thank you. So this idea have been floating around, and there are many interesting ideas being proposed. These I show some of the currently live projects. For example, maybe the US will launch this Lucy detector, which is one individual detector on the far side of the moon, either at the end of this year or maybe beginning of next year. And there are also many other big projects. Because of limited time, I will not go to individual one, but let me just mention that there is this far side and far view proposed by the US team to be built on the far side of the moon, and also the European Space Agency have committed studies on this DEX or ALO, which is also a big observatory on the far side of the moon. In China, we also have several different suggestions, including one project called the DSL or Hongmeng, which I'm working on. And we also have other suggestions, but also due to limited time, I will not go into the details. So here, I will only talk very briefly about this DSL project, or Hongmeng, which in Chinese means primordial. So this Discovering the Sky, the longest wavelengths, is a project to launch using one rocket, 10 satellites in a combined form. They will enter the lunar orbit and then release the satellites so that they form an array moving on the same orbit. So there will be one big satellite, which we call the mother satellites, which handles the data communication with the Earth. And then the other 9 satellites, they consist of 8 low-frequency daughter satellites and 1 high-frequency daughter satellite. So these 8 low-frequency daughter satellites will form an interferometer array to map the sky from the 0.1 to 30 megahertz, and also measure the global spectrum. And then there is also one individual high-frequency daughter satellite will measure the 30 to 120 megahertz band. And because it's on the lunar orbit, it avoids all these known systematics that we encounter in ground-based experiment. So it potentially can make a very precise measurement of the 21 centimeter global spectrum during the cosmic dawn. And the other 8 daughter satellites will also try to measure the global spectrum during the dark ages, although that's much more difficult. And but also they will make an interferometric image of the whole sky. And so far, we don't really have good maps at the frequencies lower than 30 megahertz. So this will open a new and probably last observational window in the electromagnetic spectrum. And of course, they will also observe the radioactivity of the sun and the planets. So I will only mention this very briefly. If you are interested, you can look at my paper, which was submitted to a Royal Society conference organized by Joe a few years ago. And this project is ongoing, and we plan to launch this in 2028. And people who might be interested in this, we are open to collaboration, and you are welcome to talk to me or other members of the project. But today, my main theme is more on the future project to be on the far side of the moon. So I just mentioned our DSL project, which is a lunar orbit array. So the advantages of this project is that it doesn't need to be landing on the moon, so that saves a lot of rocket oil. And you can also, it's easy to deploy and maneuver. And it's easy to power because you can use solar power, and easy to control the temperature because you circle the moon very quickly, basically basically 2 hours. But then if you want to build a very big array, then it's complicated because you have to maintain all of them together and communicate with each other. So you cannot go beyond it's very hard to go beyond like 10 satellites or maybe a little bit more. Even though there are such studies, but it's very hard. So if you land on the far side of the surface of the moon, it's more difficult because you need to land on the moon, and you also need deployment, so you need a rover to take them to different places. And you also need to acquire power during the long lunar night if you want to do the observation during lunar night, which is last 14 Earth days. There is a very extreme temperature on the lunar far side from the day and night, so you have to handle those. But the good thing is that they are fixed on the ground, so it's easy to maintain and operate a very large number of units. So I think what will happen is that we will first try to start with a smaller number of antennas, either on the orbit or on the far side, to try to make the image of the sky and get the global spectrum. But then we should move on to the larger antenna arrays, like a few tens or a few hundreds antennas in the next decade, trying to map some of the very low frequency objects. And finally, maybe we're going to beyond that. Trying to map the primordial fluctuations during the dark ages. That will give you the probes of the very early and the largest scales of the universe. However, how many antennas you need? I think I wrote here 10 to the 3 and 4, but in fact, from the talks you will see, it's actually need more antennas than this. But here is another paper which I already published on the second Royal Society meeting Joy organized. We have this proposal called large-scale array for radio astronomy on the far side, called LARAF. This is in collaboration with my group members and colleagues from the space industry. So we basically suggested we place a master station and 20 to 30 substations to form an interferometer array. And so each station will including a number of antennas, which we plan to make in membrane form. So using some kind of plastic membrane to minimize the weight that you need to transport. And then using the optical fiber to connect them. Presumably this can be deployed using 1 or 2 rocket launches with very heavy rockets. So the scientific objective for this kind of research, I list some of these, but mostly I want to talk about the technical problems. So you need to make the most effective antenna form and the material. So that's why we are thinking to doing it using the membrane. And also we need to build electronics that can survive and working in the lunar environment. And we also have to address the most effective way to supply the power. And we have to transmit and process the data and also deploy the array. And the effect of non-flight terrain and the underground inhomogeneity must also be considered. However, I think the problem is also that you need to work out ways to how different countries can cooperate on the moon and how to balance the scientific and the commercial interest. Because if there are a lot of activities on the far side of the moon, we will lose this very precious radio environment. But here I also show the figures showing depending on the longest baseline, what's the angular resolution that you can achieve at different frequencies, and how many depends on the number of antennas, what is the sensitivity you will get there. So basically you kind of need 10 to the 4 or 10 to the 5 antennas to really get to the stage of observing the primordial fluctuations. Although maybe you can get some other interesting scientific objects like X4 planets, interstellar medium, and AGN radio galaxies if you have fewer antennas. So here are some of our preliminary research on the membrane antenna. So we kind of thinking that we will have this using the plastic polyimide membrane and build the electronics on them. And we can then, using a rover, to make long strips of them and have these antennas on these membranes with a certain distance. And if we make the rover to go in a spiral trajectory, you will form this kind of arrays, and you have many stations together to form an interferometry synthesis. And we studied how we can supply the power to the relay satellite, to the master station, to the substations, and also to the rovers. And we considered several different sources. So these are mostly the work of my colleagues from the space industry. They are considered the solar power and the regenerated fuel cells, radioisotope, thermoelectric generators, RTG, the nuclear reactors, and also if you have some energy station on orbit, it can supply the energy using laser wireless energy transfer. And so on the right diagram, I showed that the weight required to supply each form. And as you can see in the bottom, the dark gray shows basically the other weights, and the other shows the whether you can you have a center station to handle all the energy and distribute to the various stations, or you place them individually, the powers. So anyway, so based on this study, it seems that it's just at the age of, we can basically try to accomplish it with the current technology. And so we ourselves mostly study the antenna and the receivers. So we build a model of the for the lunar regolith, and we study if we have a membrane antenna, and here actually we built one membrane antenna on the ground and tested how it works. And due to the limited time, I will not go into detail here. Finally, let me talk about the 21 centimeter signal here. So we model the 21 centimeter signal during the dark ages. We consider the effect of the mini halos that's formed before the galaxies. But we found that the mini halo contribution is very small. So during the cosmic evolution, you have an evolving 21 centimeter signal, and that's showing on the top figure. And we also compute the bispectrum. So the bispectrum, it probes the non-Gaussianity of the fluctuations. Of course, we had heard during yesterday and today many more interesting forms like the giant arcs and so on. But this is a more traditionally theoretical tool to quantitatively discuss the non-Gaussianity. And of course, there's the primordial term from the inflation or other cosmic beginnings. But then there are also the gravitational mode couplings and the nonlinear radiative terms. So we calculate them all, and we have the reduced bispectrum. So we consider the two non-single field slow roll models of inflation. One model, which is called the resonance model, for example, the axion monodromy inflation or a number of other models, basically they produce this kind of modulations in the power spectrum, like the top figure shows. And then we also showed the bispectrum in the squeezed case, where you have one side, which is much longer than the other two sides. I'm sorry, I should say two sides, which is much longer than the other one side when you form a triangle of the case, and also the equilateral case. And so we found that, in fact, in this case, especially for the squeezed case, the primordial contribution is the dominant one, so we don't need to worry too much about the gravitational mode couplings or the non-radiatives. We also consider what we call the step model. Basically, you have some kind of sharp feature in the inflaton potential so that you produce this kind of oscillations, but it's more limited in scale. So anyway, okay, so I'm running time, I'm out of time, so I just let me mention that the big challenge is that you have a very strong foreground. And so we consider two cases, whether we can, in the pessimist case, we use foreground avoidance, so we only use the mode within the foreground wedge. Or we consider the more optimistic case, where we can use all different modes, but subtract the foreground. And we do this modeling, and we also model the distribution of the baselines if we have so many baselines. So Philip Boole derived a model, analytical form of this model, as shown as the dashed lines or dot lines on the upper curve. But we also derived, for the case of random array within circular region, analytical formula, and that's shown as the solid line. And we show that if we have a single or double or triple stations, what the signal to noise ratio look like. So anyway, so we obtained the noise power spectrum. You can see at very high redshift, it's very strong, much stronger than the 21 centimeter signal power spectrum. So as a result, even though we have a very large number of observable modes, when you take into account of the noise and within a very limited observation time, for example, 100,000 hours, which corresponding to about 11 years for operational, the effective number of mode you can actually observe is still limited. Anyway, but you can detect them, but it's just limited in some sense. And we obtain the constraints on the spectral running and the resonance model parameters on the step model parameters. And okay, I think I'm using up my time, so let me just stop here. Thank you very much.
So we have time for a quick question.
No, we don't have time.
No.
Sorry, we don't. Oh, okay, well, you know.
That was very interesting, thank you. You mentioned the number of master stations for the array. How many antennae per master station could you envisage? So what would be the total number of antennae?
I mean, we can make all different numbers and calculate. In this study, we kind of assumed like 1 million antenna per station.
So, sorry, 1 million total or 1 million per station?
1 million per station. Yeah.
Okay, thank you very much. We go to the next speaker. We are a bit in a hurry.
Yes.
Andras Kovacs, and his talk is Cosmic Voice as a Probe of Large-Scale Structure and Cosmology.
Okay, if you could, that should.
Yeah, now it's working.
Brilliant.
All right, thank you. Hello, everyone. So my talk is about one specific, title suggests otherwise, but my talk is about a rather specific application of cosmic voids in cosmology, because one could do many things with them, right? Just analyze, just cosmographically to detect them. Study galaxy evolution, voids versus field galaxies, or studying their size distribution as a function of cosmology, probing modified gravity, simulations, data. There are many things to consider here. But my favorite application, and that's basically what in our group in Budapest we have been doing mostly in the past years, is to use them for CMB cross-correlations. So in particular, study two things, because as the CMB photons travel through the universe and the local cosmic web, necessarily they are reprocessed by these large-scale structures, as we know, including also the cosmic voids. And for our applications, two things are most interesting: CMB lensing effect, so like some deflection near the cosmic voids for the CMB photons, and also the integrated Sachs-Wolf or ISW effect, which depends on the time derivative of the gravitational potential, which is a kind of smoking gun signal of some kind of dark energy, right? So if the dark energy is stretching a little bit more the gravitational potential of these voids, and there will be a net difference in temperature between entering and exiting these large-scale objects. So it's interesting because it gives you a different handle on... Yes, that's right, exactly. Yes, exactly. That's a good clarification, yes. And I give you this simple example first, like this is the CMB cold spot. And we have heard in the morning from Daniel that actually this is an interesting object on its own, this super void, this Eridanus super void that's aligned with the cold spot. And we knew this before doing this analysis with the dark energy survey data, because even from galaxy counts, we sort of knew that there is an underdensity of galaxies there aligned with the CMB cold spot. But then I led a project as a DES member because we realized that actually this cold spot area was covered by the dark energy survey. And our colleagues in the DES team, they created from about 100 million galaxies this very nice gravitational lensing map reconstruction based on all the shear catalogs and the whole DES pipeline. And then we asked the question, using this lensing map, how this cold spot area looks like, and this was the answer. That appears to be the most underdense part, at least of this tank-shaped footprint of the DES data. So again, now it's not just galaxy count, and as we heard, it's not just the velocity field implying some sort of a void and a repelling region there, but also gravitational lensing. So it's very reassuring to see this correspondence between the probes. But, and that's the important question, that can we really explain the cold spot by doing this? And the answer is, well, not really. Because if you do the details of all this, then, of course, in lambda CDM or in your favorite model, you can calculate the effect, this kind of ISW effect from a void like this, which can be fairly big, like 200 megaparsecs in radius even, but fairly shallow, like 20-30% underdensity. And given that combination of extremeness and radius and underdensity, what you expect is not what you observe. Basically. So you would need either a bigger void or some other cosmology from this size of a void to fully explain the cold spot. So we don't really have an explanation. But, and that was also a good development from the dark energy survey data analysis, we also analyzed 100 other super void regions in the depth footprint, smaller ones, higher redshifts. So statistically, we stacked this signal, and this is really what this plot is showing. So it's not just this particular super void aligned with the A cold spot or D cold spot in the CMB, but like 100 of them also are giving us, if you analyze this as a profile, this is the lambda CDM expectation, giving you as a stacked signal something like -2 microkelvin, which was backed up by a series of theoretical calculations by other teams, so that we know that linear ISW can give you something like this in lambda CDM, while what we observed previously in SDSS and BOSS, and then also in DES supervoids was like this. And I'm just showing here model X because we need some explanation for this, that at least the largest voids are giving these anomalous signals for us. And that's basically the summary of a long summary of the motivation, why are we interested in doing this. And I'm just going to list you like 3 different areas of improvements that we have been doing recently, which is check what's going on with CMB lensing, which could be another counterpart to resolve this tension maybe. Go to higher redshift, because by analyzing SDSS and DES data in combination at low redshift, basically we have run out of data to analyze, because precision won't help much. And then also improve the modeling and see what's going on with other cosmologies. So for the CMB lensing probes, we did a new analysis with the Pan-STARRS galaxy catalog combined with WISE in this rather conservative survey area, about 14,000 square degrees, using luminous red galaxies, led by mostly Uri Courier scientists about 2 years ago. And then we wanted to check, okay, we also can find voids in this data set, and what do they give us in CMB lensing? And the answer is, after also understanding better the mocks and how to create realistic mock catalogs for this, the answer is that there seems to be no tension, no big anomaly in the CMB lensing of not exactly the same voids, but voids defined in similar ways. And this is what this beautiful agreement between the mock, the dashed one, and the WISE PS1 void cross CMB lensing shows you here, or at the image level. And also on the right, you can see that there is no big anomaly when you divide between north and south patches, small voids, big voids. If anything, there is a slight redshift dependence in this, but also that's not really significant. This A kappa here just gives you basically the 1, meaning the baseline lambda CDM expectation. So there is no real anomaly. Then we continued, and also I was involved in this DESI legacy survey analysis led by Simone Sartori and the team mostly based in Marseille. And then we used the whole DESI area already, like the imaging survey and the luminous red galaxies which have good photometric redshift to detect at least these largest voids. So we used this data again to do the same thing. And what you can see here, well, we also have some rings, okay? Simulations versus observations. That we managed to improve the mock making, pipeline, assignment of photometric redshift, accounting for systematics, and for different kinds of voids with no compensation or significant compensation around the voids as a kind of matter shells. So for different void types, and what you can see here is for different redshift bins and the different void types, we don't really see any anomaly. And also the nice thing to see here is that by incorporating more and more data, of course, we have better and better statistical precision. So we managed to bin the data very nicely. And again, the results from CMB lensing are very consistent with the expectation, which is, in a way, good to see. Another line of investigation was that, because as I said, that we didn't have much more data to consider below redshift 0.8 or so. So we asked the question, okay, can we maybe use quasars, clustering of quasars, to find the biggest voids? Well, this is a sparse tracer catalog, but at least it could be good to map out large-scale voids or large quasar groups, as traditionally has been done in multiple examples. So we realized that there is this very nice new quasar catalog from Gaia called Quaya, put together by this team, mostly based in New York. And then basically the thing was that the Gaia team provided a raw catalog of quasar candidates, but it wasn't particularly clean for cosmology. Photometric redshifts were not really good, so this team cleaned things up, applied more color selection and even some sort of proper motion cuts, so whatever didn't move for Gaia was a quasar, first approximation. And then they put together this very nice quasar catalog with about 1.3 million quasars with decent redshifts or photometric redshifts to study large-scale structure. And this is what we found. So like with the usual void finder tools, one of them was called Zobov or revolver algorithm, which is based on Voronoi tessellation of the density field. And what you are looking at here is work done by Nestor Arsenov, who is a PhD student working with us. And here is a very thin slice of this quasar catalog, and the colors indicate like local quasar density, inverse of these Voronoi cell volumes. So you can see some sort of like blue quasars are more isolated, and the red, orange ones are more in clumps. So with this Quaya catalog, we were able to do this sort of mapping, and again, building catalogs of, well, not just voids, but also clusters with some definition or quasar groups with Quaya. And what you can see here is also that we used a lot of mock catalogs. I think here we used something like 100 or maybe 50. Incorporating also, again, these observational systematics and other potential problems with the selection effects with the data. And what you can appreciate here is that these kind of data points and the solid lines are the mean and standard deviation from the mock catalogs. And the colored histograms are the size distribution of voids and clusters or quasar groups that we found from the data. And you can see the maximum size for the clusters is about 140, 150 megaparsecs over age. Voids are typically a bit bigger. And this is very inclusive, because then, of course, a lot of the small objects should be just noise, because this is close to the actual typical mean separation in the catalog. But we provided the data, nevertheless, for people to explore. This is publicly, both the quasar catalog and our sort of value-added catalog is publicly available now. So the third interesting thing that we have been working on is that, okay, so because historically the typical approach was people estimated, including us, the signal for a baseline lambda CDM cosmology or a few mock catalogs. But this is not anymore really meeting the standards of the field, so we also wanted to improve and do this for hundreds of catalogs and for very different cosmologies. And maybe some of you are familiar with this mock environment or simulation environment in WCDM simulations called the Gower Street mocks, coming from UCL. They simulated almost 800, I think 1 gigaparsec boxes, which is, for our kind of science, fairly small actually, but still, this is a very nice suite of simulations, varying all like 7 WCDM parameters simultaneously. And originally it was also used within the dark energy survey to sort of do map level inference instead of power spectra or other kind of traditional analysis. So we just took these simulations with Mina, who is a PhD student working with us at the Concoli Observatory in Budapest. And then we did a kind of ray tracing analysis in all these different simulations, and created ISW maps for the full sky, of course, because in simulation we have access to that with perfect redshift, everything. So for all these hundreds of different WCDM models, we created these mock ISW maps, okay? And then the colorful plot on the right is just showing you that compared to the baseline, like lambda CDM or Planck-like lambda CDM signal or simulation, because they also do have examples of that, as a color coded by the W in the WCDM model, and this is omega m, what's the strength of the signal, right? And you can see that, of course, lower omega m implies higher dark energy presence or density, and in combination with some trends that maybe the quintessence side of the WCDM modeling gives you typically stronger ISW signals, maybe we can cook something out from this. At least we wanted to do this systematically to improve also our modeling tools. And this is where we are now, more or less. So of course we want to play the same game now. So in all these different lambda CDM mocks, WCDM mocks, we can find voids, full sky, later add in systematic effects to make the simulations Euclid-like, DES-like, whatever we want. And then this is what we are building, a sort of template bank of stacked ISW profiles for these like big voids and super voids, and see how the different dark energy strength in particular like affects the strength of the signal, because I didn't have much time to talk about this, but of course the problem is that it's very hard to agree on a good void definition, and what we are working with is typically voids defined in 2D slices, which is very hard to model from first principles, so we need to really to simulate. And this is what we managed to do. So we have some good candidate models, even in the WCDM framework, to explain some of these enhanced ISW signals. But the good news is that there is on the way a Gower Street 3.0 version, which will also incorporate W0, WA CDM cosmologies, so we can even check on the DESI preferred cosmologies if we want, or further improve this modeling. So as a summary, I can still say that there are some tensions in this business that we are doing, these voids being cross-correlated with CMB lensing or temperature fluctuations, and especially the largest voids, the super voids, are showing some anomalies, which is interesting. And while we are waiting for big data and build bigger and bigger collaborations, it's good to see, in my opinion, that even with existing data, which are typically public, there's year 3 or now year 6, or legacy survey, Pan-STARRS, WISE, and Gaia, which was clearly unexpected, you can still do improvements and useful cross-checks. And really what we are waiting for now and what we are working on now is also Euclid analysis with simulations, Rubin, Roman, and DESI data in general, and the voids extracted from these surveys. I'm sure they will help us answer these questions with even better data. And I think I stop here, and thank you for listening.
Yeah, that was very interesting. Thank you. You show on your quasar results. You showed this beautiful structures. Have you made a comparison with the CMB? Because Soltan has a claim there is, with a very large quasar catalog, he found a significant signal from ISW.
Yes, what we are trying to do first is more like a power spectrum or two-point level analysis of that, cross correlations with CMB lensing and or temperature. Like, signal expectation is quite low, it's a sparse catalog, but we want to establish first that. And also we were cautious because, as I said, that just naively stacking maybe with all the structures in our catalog could be risky. So first we want to, basically the logic is first to use maybe the CMB lensing map stacked to really determine above which radius we can really talk about robust structures. And then we can do maybe the ISW measurement, but we didn't want to rush into that. But yeah, it's on our agenda.
Can you comment on Soltan's result?
I don't think I remember.
He had 1 million quasars.
Yes.
One-ish, 1.5.
But there, the stacking, was it based on kind of large-scale structures?
I don't read the paper, but he claimed a significant ISW excess from the quasar.
I'm not familiar enough with that, but also I don't have a slide for that here, but from the EBOS quasars, we were also doing some preliminary analysis of this kind, and we also did see some evidence for correlations at least, ISW or not, I don't know, but between 0.8 and 2.2 redshifts, which also looked interesting, but I should look it up, this paper. Okay, thank you.
So if there are no other questions, we then ask you again.
For those of you that have read signed up for the conference lunch, we're going to meet in the foyer and then we're going to walk together to get to the coach for lunch. So please stay in the foyer, gather there.
Just going to get me jacket. You mean the foyer here?
Yes.
Right.
Throat back
Something
high
like
enough to hear it. Yeah, that would be
Okay.
perfect. And then this points.
Okay.
Hopefully, I think that's everything.
These points.
Starting 5 minutes late.
Okay.
So
Yeah.
got into that. Okay, folks, after that excellent lunch, thank you to our hosts. Ready to start again. We have one keynote talk and 3 short talks. And the first one up is Francesco, will tell us about, you can read it on the slide. So Francesco, I'm going to go and sit down there. If I come down here, that's when you stop.
Okay. So, okay, thank you very much for the invitation. It's a pleasure to be here. And I will talk about recent results about the correlation and anisotropies in the first data release of the DESI. So this is the outline. So I will make a brief introduction about large-scale structure and quantitative characterization, and then I will talk about DESI DR1 and then my conclusion. Okay, so the story, at least for what concerns me, started with the analysis of the first data release of the Redshift surveys. This is a Center for Astrophysics 1 and 2. Then we had the 2 big surveys. One was 2DF. 2DF had, we have the 2 different kinds of Redshift surveys. On one hand, we have something like CFA2 and CFA1, which cover a large contiguous angular region in the sky. And the other ones are like 2DF, which instead cover, say, a small area in the sky, but they are much deeper. Okay. The Sloan instead has both characteristics. That is, it covers a very large contiguous area in the sky, and it's much deeper than CFA2. And indeed, we can see the Sloan Great Wall, about which this morning Daniel told us about. Then we have another 2 Redshift surveys. One is Wiggle Zeta, and the other one is Vipers. These are like thin pencil beams, and so these are not very useful from our point of view, because we instead, as I'm going to explain later, we need a large contiguous area in the sky. So then we have these other structures that are seen in a different way from the galaxy distribution, which are very interesting, but are not, say, useful for characterizing correlation properties directly. Okay. So the first one of the first papers, I would say the first one about the possibility that there are large-scale structures, was the paper by Gérard de Vaucoulet in 1970. And in this case, he was using number counts as a function of magnitude to find out these structures. Okay, then there were, of course, different kind of statistical tools have been used to characterize statistically these structures, and clearly the tool was developed when more data were available. Just to make an example, CFA1, CFA2 had few thousand galaxies, while Sloan had something like 1 million, of the order of 1 million, but actually, say the samples, finally, the useful samples were of order of 100,000 galaxies. Okay, while then clearly when the statistical properties of the samples were improved, also the kind of analysis that one could do has changed. So while, for example, at the beginning one was measuring only the angular correlation function, then one passed to the two-point correlation function, then the conditional density, and then the conditional density is the first moment of the distribution. Then one can study the full probability distribution function of the counts, for example, of the conditional counts. And this has the main information about the statistical properties of the distribution. Then recently we have introduced also this angular distribution of piecewise distance, which is a refinement of the PDF of counts. Okay, there are many people that have been studying, say, the transition to homogeneity, and I mean, I've just cited some of them, and say the difference between the results are very different. Somebody finds the transition to homogeneity is at 20, at 50, at 80, more than 200, depending on the sample and depending on author. So why there is this difference is that there are different, say, way of treating the sample, and different definition of the homogeneity scale, and different, say, statistical tools to define the transition to homogeneity. Okay, so from our point of view, it is very important to use large contiguous angular coverage, so redshift samples with large contiguous angular coverage. We have to control the luminosity selection effects. No? Somebody says that cosmology is the science of selection effects. And I think it's right. And control the boundary effects, clearly use unbiased estimators, then clearly define what is the homogeneity scale, and then the last point is to say, test the stability of the statistical stability of the results inside the single sample, because there can be problem of self-averaging. Okay, so this is the first, the early data release of DESI. Again, even this survey is made by very thin pencil beam, which are quite deep, but then the first data release has covered, say, a rather large contiguous area in the sky, at least in this part. The second one will have a much larger angular coverage. I think the new data will be published next June. So there are different samples in this survey. We will focus on the bright galaxy sample, which is this green part, and in the luminous red galaxy sample, while we will not use the other samples. Okay. So these are the four key points: boundary condition, unbiased estimator, luminosity selection effect, and self-averaging. Okay, luminosity selection effect, these are important when considering the bright galaxy sample, because the bright galaxy sample is magnitude limited, so one has to construct samples which are volume limited, so which are complete up to the apparent magnitude limit of the survey. The luminous red galaxy instead is a quasi-volume limited sample by construction, because one selects a certain kind of object with more or less constant absolute magnitude. So the treatment of boundary condition, there are two parts. Okay, one must have contiguous angular region and fully described volumes. Okay, why contiguous angular region? Because we need basically a volume which we can put inside complete spheres. This is our aim. To do that, we have just say, select the most complete part of the first data release Daisy, which is this part, this violet part here, which we have estimated the completeness is larger than 95%. Okay, these are two samples with different depth and also different thickness. So this is why this looks more uniform, just because the thickness is larger, and so this is an artificial projection effect. But here, for example, one can see very large scale structure. Okay, then the second point is to use boundary, so how to treat boundary conditions. So the point is very simple. If we use a sphere, so we compute the correlation up to a certain distance, and this distance is fully inscribed in the sample volume, then we are safe. If instead we have a situation like this, in which part of the volume goes outside, then if we take it to be representative of the whole sphere, we are making the assumption that what is outside of the sample is similar to what is inside. So it's a way of isotropization of the signal. Okay, so what we do then, we compute this statistical quantity here, which is the n of r is our stochastic variable, is the number of points in a sphere of radius r. And then we calculate the distribution and the average and the variance as a function of scale. So these are the estimators. So this is the number of points, this can be the density. Okay? That's the number of points around the galaxy, the I galaxy. Then we can estimate the first moment, the second moment, and so on. So the test is very simple. If the distribution is Gaussian, the density is constant with scale, and the variance goes like 1 over r cube, then the distribution is uniform. Instead, if the probability distribution is non-Gaussian, the density has a power law behavior, and the variance decay is lower than the Poisson, then it is inhomogeneous. Okay, then clearly the homogeneity scale depends on how one, say, define exactly the transition from power law to flat. But okay, this is say, a second order problem. The first order is to see whether it is a power law or whether it is a constant with scale. Okay, so if there are correlations, in general, we expect that there are deviations from a Gaussian. So, for example, which kind of deviation? Okay, the Gaussian obeys to, say, a universal, there is a universality class of systems which behaves as a Gaussian. The Gaussian here is the black line. If we go outside the central limit theorem, so in the case in which there are long-range correlations, we can have very different kind of distributions that we can, say, summarize with these two kinds. One are the distributions which have a power law tail. Power law tail means that there are moments which diverge. Okay, and the other one is a gamble. The gamble is something in between a Gaussian and a distribution. So what does it mean, this tail? This means that the fluctuations which are far from the most probable one, which is the peak here, are very probable. Okay, while in the Gaussian we don't have this. The peak, then we have very fast decay of the probability density. Okay, for a gamble, the situation is in between. So why I talk about the gamble, because finally this is the best fit to the data. So that's why the gamble is this is the normalized function, and it has two parameters, mu and beta, which are related to the mean, which depends on scale, and the variance, which again depends on scale. Okay. So then there is another test that is important to do, is to see that inside the given sample, if we the distribution, the probability distribution is stable. Because if we have a situation like this, this means that the properties are not the same in two different parts of the sample. Okay, this is just to have an idea why we are interested in this situation. In this case, the probability distribution is defined everywhere, it's the same. Even in this case, we have, because the size of the structure is the same everywhere. So even if this distribution is much more fluctuating than the other one, the probability distribution is again well defined. In this case, instead, when there is a single structure which dominates a part of the sample, then one has to ask the question whether the distribution is self-averaging inside that sample. Okay. And that was indeed the case with the data release number 6 of Sloan, in which you can see by eye that if we divide the sample in this way, we have a large-scale structure here, and we don't have it here. So this means that the properties on such large scales are not self-averaging, while at small scales they are. Okay. And this is what indeed we found, that if we go, for example, in sphere of 20 megaparsec, more or less the signal is the same. When we go to 40 or even 60, 80, we find that the distribution has 2 peaks. So this means that the average value is not well defined inside at that scale. Okay. So, okay, taking in mind this problem that we found in Sloan, this was a result that we got in 2009, in which the distribution was found to be well fit by a gamble at different scales, okay, from 10 to 80 megaparsec. This is the R1. Again, we have fitted the gamble, and as you can see, in samples up to 300, 400 megaparsec, the gamble is very well approximated by the data. So clearly, when we go to large scales, we have also 2 other problems to be considered. The first one is that the number of centers over which we make the statistics as a cutoff, because clearly when we go to scales such that the size of the sphere is as large as the sample, we have only one sphere that is as big as that. And so we have this kind of cutoff. And then we have also another problem, is that there is an overlapping factor. So when we go to large scales, we are basically sampling the same part of the survey. So we are not making a real average in different regions. Okay. This is why we have to care about this, because clearly we expect to see deviation from sample to sample, so depending on the size of the sample. Okay, so the idea is that, okay, these are finite size effects. When we enlarge the volume, that is when we go from red to blue to green to orange, then the approximation to the say correct distribution will be better. Otherwise, there is a tail which is due to the fact that we are not. So again, here we go, this is a sample of 400 megaparsec. This is WL5, which is the largest sample of the bright galaxy sample, and this is the luminous red galaxy sample, which has a much larger volume, and so which, in a way, sample the distribution better. So these are the results. Again, this is for Sloan, the old samples. And these are the new data for DAISY. Okay. In Sloan, concerning the average, in Sloan we have found that the say small scale up to 20, 30 megaparsec, the average density was decaying in this way, and then we had this tail, and okay, we didn't. Our say conclusion was that we don't know whether this is really a change of slope. For example, Hogg Einstein concluded that this was a change of slope at about 70, 80 megaparsec, or whether this was a finite size effect, due to the fact that due to the lack of self-averaging properties inside these samples. Okay. When we go to DESI, which have a much larger volume, we see that again, if you see the tail, the large scale tail, you see that it deviates a bit, but when we go to larger and larger sample, the power law looks to be better defined. Okay.
Are you choosing the galaxies at random that you centered the sphere on?
Sorry?
This galaxy which the sphere is centered on,
Yeah.
are you choosing that?
No, we choose all the galaxies. Yes. And this is the average. All the galaxies such that the sphere centered on that galaxy is inside the sample volume.
Show the range on each data point. There should be then a range of possibilities.
Yes.
That is not being shown in the figure.
No, sorry, I didn't get what did you say?
For any particular scale, then you would have put your initial point on any one of the galaxies in the volume.
Yes.
Each one returns a slightly different answer.
Yes.
So then don't I expect a certain uncertainty?
Yeah, okay, the error bars are very, very small. The error bars on the average are very, very small.
Oh, I see. That point includes
Yeah.
the error bar.
Yes, exactly. Yeah. Okay, and the difference in amplitude is just due to the difference in the luminosity function, because one is selecting, so these are very bright galaxies, so they are much less very bright galaxies than faint ones, which are the blue ones. Okay, lambda CDM instead should show a clear transition to homogeneity, depending on how we define that between, say, 20 and 40 megaparsec. So the exponent is exactly equal to 3. This is the variance, and again, the variance decay is lower than 1 over R cube, which is for an homogeneous distribution, and this is the variance for DESI, which is, it is in this region here up to 10, 20 megaparsec. This is just due to the fact that the sample is sparse, so this is just due to the noise due to the nearest neighbor distribution, but if we go to large scales, we find that the exponent is minus 2.4. Okay, so this is our conclusion. So the PDF is described as a gamble, the density decays as a power law up to 400 megaparsec, and the variance also decays as lower than Poisson. Okay, then we will have much better data very soon, at least in 2 or 3 months. The second data release will cover a much larger contiguous angular region, and so we will be able to reach larger distance in depth. So another say, a complementary study that we did was not only to look at the inhomogeneity, the spatial inhomogeneity, and so the correlation between galaxies, but also trying to characterize anisotropies. Okay, so we know that there are many anisotropies have been studied by many people in very different way using very different samples, and so our idea was, okay, let's try to consider, say, a new statistical tools that has, it's very convenient because it allows to characterize directional structure without assuming any specific form of anisotropy, like, for example, dipole anisotropy, quadruple anisotropy, and so on. And is also model independent, okay? So we don't have to make any a priori assumption about the kind of anisotropy that we are to, or there are no free parameters in the story, so in the statistical tool, okay? There are nothing, just, it's very simple statistical tool, which is, okay, we sit on a point, and we measure the distance from all the other points, and we consider the distance and as a function of angle and distance. If it is isotropic, this probability is normalized to 1 over pi, okay? So, for example, just to give you an example of how does it work, these are just sticks in 2 dimensions, and this is what we measure with the angular distribution of pairwise distance. So this is the angle, and this is the distance. So these are sticks of same distance, and you see here that the distance is the same, is about 80 megaparsec. And then they have different angles because these sticks have different angles too. So it's very useful. Then we can construct the angular variance. The angular variance has a very simple interpretation. If we have a Poisson distribution or an isotropic distribution, this goes like 1 over r. Instead, if there is a correlation, then there is a correction, okay? For a CDM, what do we expect? That this correction is 1 over r, so it's like Poisson at small scales because n is equal minus 2, and then it is again 1 over r because n is equal 1 at large scale, okay? Because clearly 1 over minus 1 over r to the 4 decays much faster than 1 over r, and so again the dominant term remains Poisson. Okay, this is what we expect for a Poisson distribution. So this is just a two-dimensional slide. We can also do in 3 dimensions, but in 2 dimensions, the statistical tool has a very straightforward interpretation. So we finally decided to do the analysis in 2 dimensions, even because the survey, in 2 dimensions, the survey allows to sample a much larger volume of space. Okay. So this is a Poisson in which basically you see that there are no structures. This is instead DR1, one of the sample of DR1, in which you see that there are this big structure in this plane, okay, up to 200 megaparsec. When we enlarge the sample, we see that the structures are present up to, in this case, 500, but we can also go to 1000, okay? And so basically, if we measure the angular variance, instead of getting a signal that should go like 1 over r, we find something which is more or less constant as a function of scale. Then clearly, this tail here is due to the fact that we are feeling that the sample is finite. Okay, so the number of pairs decreases when we go to large scales. Even for a Poisson, we find that there is a deviation from what we expect. For a Poisson, we can also compute analytically what is the deviation. Okay, so given that we can reach distances of 500, 1000 megaparsec, we can ask the question of whether these results are compatible with what is expected with cosmological models. Okay, we can use, and actually we did it, even though I didn't show the results now, model simulations to test that. But then just to make it more simple and also maybe more intuitive, I would spend some minutes about the property of superhomogeneity. Why? Because basically we want to relate the initial, say, the early times density field to the late times galaxy distribution. This is the aim of any cosmological model. So the problem is, okay, which are the fundamental properties of the early time cosmological density field? So we know that in general we have 3 different behaviors of the power spectrum for k that goes to 0, which means that for distance that goes to infinity. Okay, we can have a case in which the power spectrum diverges, one in which the power spectrum is constant, and the other one in which the power spectrum goes to 0. Okay, so in statistical physics, the case in which this diverges is called self-similar distribution or scale invariant distribution. So there is a bit of confusion in terminology between statistical physics and cosmology, because in cosmology, scale invariant is used to describe the Harrison-Zeldovich, which is k equal to 1. Okay. So in this case, instead, the correlation length is finite when the power spectrum is constant. And in this case, instead, the power spectrum, the distribution is called superhomogeneous or hyperuniform, as Torquato called it. And this is a quasi-crystal, so it's something more ordered than a Poisson. Okay, why we need that? This was in this paper by Harrison in the 70s, he showed that in order to have a distribution of fluctuation which is compatible with the Friedman metric, so which doesn't induce, say, the fluctuations in the gravitational potential that will break the metric, one must have that the power spectrum goes like K. The power spectrum goes like K means that the distribution is super homogeneous. Okay. So these are just to have a visual impression of what does it mean. This is a scale invariant. Scale invariant means that the correlation length is infinite, so means that the system looks the same at different scales. This is a Poisson, so this is correlated at small scales and then Poisson on large scales. So there are structures, but these structures have a finite distance, and then a finite dimension, and then this is instead a super homogeneous distribution, which this is something like an ordered distribution, but say it looks like a lattice of lattice, if you like. Okay. So again, if we look at this distribution with the angular distribution of pairwise distance, we see something like this, so completely structureless, which is very different from what we observe. Okay. Okay, so what is the implication? The implication is that at least for the size of the samples that we have studied up to now, but clearly, according to the result by Alexia, even probably on larger scales, we have to go from a situation in which we are using the cosmological principle, so that is the statistical homogeneity isotropy about any point, to a situation in which the distribution can be statistically, say, isotropic, but not homogeneous, which is so it use instead of the cosmological principle a Copernican principle, okay, absence of any privileged location and direction. So what does it mean from a theoretical point of view? I mean, there are many attempts to study these kind of inhomogeneous models, and I am not an expert of that, but I mean, once we made a simple model using the Tolman-Bondi metric, which is a spherical symmetric metric, but then clearly I find very interesting a work by Thomas Booker about back reaction, or by David Wilshire about this timescape where, I mean, time flows in different way according to the local density. Okay, these are some references, old papers and new papers. I can stop here. Huh?
Questions?
Yes.
So in your test of larger scales, you measure this power law of as a function of R, right?
Yes.
But for the lambda CDM, one should be able to predict what it looks like. Has there been any prediction?
Yes, lambda CDM is.
You had that on the plot.
Yeah. I mean, basically, lambda CDM is, here is. So it flattens at around 20 megaparsec, because that's the size of the largest inhomogeneous region that you can form in the time that you have in these models.
Sorry, but by lambda CDM, you mean lambda CDM with the assumption of Harrison-Zeldovich, right?
But lambda CDM has inside Harrison-Zeldovich, yeah. But okay, but this is a very simple calculation. It's just sigma 8, if you want. I mean, it's the scale at which fluctuations becomes of order of the mean.
Yeah, but sorry, but is this just a theoretical calculation, or you have tried it with?
This is a simulation, yeah.
Yeah, but with simulation.
Yes. And they agree, of course, because.
When Mogg et al. Saw this flattening with the SDSS-DR4 data, that was at a slightly higher scale.
Yeah.
And you are ascribing that to finite size effect.
Yes. if you see.
Is there a clean way?
Distribution of this test here, you can see clearly that there are these problems, okay? When you consider the average, those scales, so one has to put a question mark. Is this really an average, or is the average is really representative of the statistical property of the samples, or there is a problem of this kind? So the distribution is not self-averaging. Say, at that time, in 2009, our explanation was that this was something to be considered. Okay, and then now this problem is over because we have a sample which is much larger. So.
You just going back to that other plot with the flattening at 20 megaparsec. So this flattening at this scale. So because often I sort of talk about how structure is a little bit not very well defined. So with this 20 megaparsec scale, is that also restricting? Is this based on, like, when you're talking about something extending that side, is this based on a number count, a density, something physical about this scale? I just was wondering if you can clarify.
See, the normalization here is done that you start your simulation, I don't know, a redshift 50, 100, whatever, and you normalize the power spectrum with what you expect given the CMB. Okay, then you start the simulation, and then you let the simulation evolve, and you create this kind of structures, let's say. You create structures up to 20 megaparsec. The structures that you see on larger scale in the simulations, which are there, I mean, I'm not saying that there are no structures, but they have small amplitudes. Okay?
Based on an amplitude?
Yes.
Gaussian, right? But there are models with non-Gaussian.
Yeah.
People are interested in inflation and predict.
Yeah.
Understanding is a shorthand for saying something with the Gaussian. I agree with you that one can separate the matter content and the geometry from the power spectrum.
Yeah.
People say lambda CDM, they usually mean the whole Monty, right? It's the power spectrum plus the.
Yes and no. Okay. Let's leave that for coffee. What I wanted to say is that if you try to use some lambda CDM with the power spectrum, which has some non-Gaussianity, introducing
as far as I know, I mean, you can change.
I mean, the CMB, there are limits now on Gaussianity, but
I don't think that you can. I don't think that you can obtain a factor 10. Maybe you can obtain a factor 2 in distance. I mean, that you can form a structure up to 200. Maybe you can change from 20 to 40 to 10. I mean, changing these parameters. But
Margot, Lev Kaufman used to say there are as many kinds of non-Gaussianity as there are kinds of dog. So what is constrained is
no elephants.
Sorry, you had a question, and then do it.
So thank you for the presentation. At some point you introduced the Gumbel distribution. Is there a way to theoretically understand where that's coming from?
we tried, but I mean, in general, Gumbel comes from extreme statistics. But I mean, this is the example that are known in the literature, indeed. But I don't know in this case what can be why it should be like that. So I don't have an explanation.
Very nice talk. So I have two questions. First question is, you're using R, but the data is given in Z. You can go from Z to R, you have to assume a model.
Yeah, sure.
So it's very, to me that's quite decisive, because in some sense you're using a model which is based on homogeneity and isotropy to go from Z to R, and then you're using that R to say that this model is Z. So what is the effect of that?
Okay. So the idea that we are in a range where relativistic effects are not important because we are up to 0.1, 0.2, I mean 20 megaparsec is something which you can just assume that redshift is... Huh? Sure, but I mean, if you assume lambda CDM or any other model, it doesn't change more or less. It changes second order, not.
And then the second question is, when people look at DESI, for example, you are having this density correlation and you have got the BAO peak. Now, I don't know where in your, now, in some sense, I should see a peak, there is a scale, there is not a scale there.
No, indeed.
So where is that peak?
With this method, you don't see any peak. Yeah.
I don't see any peak.
I know.
It's only a 1% change in the correlation function. You don't see it with this.
Yeah. But of course, I mean, if it is not homogeneous, for sure you don't have baryon peak.
But Franco, to come back to what I asked earlier, as you go to larger and larger scales, what you are literally doing is you are putting spheres in the survey volume of that radius.
Yes.
So as the scale gets bigger, you can put in fewer and fewer spheres.
Yes.
Which are entirely contained
Yes,
in the volume.
right.
Because you said you're not going to let them go outside and
Exactly.
simulated data.
Like
so
this.
why don't I see the error bars going up as you go to larger and larger spheres? Because there are fewer.
Okay.
The gradient should go up.
Yeah, okay, yes. Probably, maybe these are, they don't have error bars.
So do you do a jackknife
But
analysis?
yes, yes.
Pick them at random? And
I did bootstrap in general. Yeah.
Okay, sure.
But okay, they are not shown here, I think. Yeah, you are right. But say, the error bars are becomes say relevant in this region, in the tail. Okay.
Because that's the crucial region.
Yeah, sure.
These bigger Z people, they let the sphere go outside the survey volume.
Yes.
And they filled it with data from a random simulation, which is isotropic and homogeneous by construction. So they fed in the answer into their, and they say, they get 3 for the dimension, but that's actually their model, not the data.
Yeah, exactly. Yes.
Please.
Regarding these observational issues, do you think that, for example, redshift distortions can affect your results?
Well, yeah, redshift distortion again are localized at very small scales. I mean, cannot be relevant at scales of order 100 megaparsec because of program velocity, they don't exceed a few thousand kilometers per second. So they have an effect, but at small scales.
Looks like you've satisfied everybody. Remarkable result, and
thank you.
We are even ahead of time, so let's thank Franco again. 10-minute break, but please be back 5 minutes, 3:25, so we can give a little more time to the next speaker.
Just please send me out. To your data.
Yes, yes. Let me, I think, yeah, let me just, because I've realised I need to just get everything set up. And also,
there are various files, few files in this. One called Preston is the one.
Okay, thank you. I'll get it set up ready to go.
Yeah.
I'll get the next.
But you
yes.
take a copy? Or you want the pen?
I'll plug it in, I'll take a copy onto the computer and then I'll give it you back.
Oh, yeah, yeah.
In just a minute. Thank you. And then
Yeah, sure.
thank you. Let me just Right. as well.
Okay.
Yeah, I think everything's good.
Great, thank you very much.
Okay, now you have a short talk by Jionu Kang on constraining inflation models with spinning points. That's a new one.
Okay, hello everyone, I'm Gonu Kang, and today I'm glad to have an honor to present our recent study, Constraining Inflation Model with Spinning Voids. To begin, let's talk about what void is. The cosmic voids are largest extreme underdense regions surrounded by filament and sheet. And due to their unique and underdense conditions, voids are not very much affected by late-time nonlinear evolution of the universe. And that makes void to be highly sensitive to the initial conditions of the universe. Also, I want to introduce about the running of the scalar spectral index, which is alpha S. And it is one of the most important proxy to understand the early universe in inflationary stage. The mathematical meaning of alpha S is the scale derivative of spectral index NS. As you know, the lambda CDM uses vanilla single-paired slow roll inflation model that predicts a primordial density power spectrum with a scale-independent spectral index. Means alpha S should be exactly 0. However, recent observations are challenging these simple assumptions. On one hand, Raman alpha forest measurements from EBOS have detected a significant negative alpha S at small scale. On the other hand, recent CMB measurement from ACT DR6 hints a positive alpha S on much larger scales. This inconsistency leaves us with a critical question. Are we seeing a truly complex, non-standard primordial power spectrum, or it's just disagreement between CMB and nonlinear late-time effect? To figure out, we desperately need a new independent diagnostic measured at different scales, free from astrophysical complications. To test if voids can act as this independent diagnostic, we utilize the Abacus Summit N-body simulation. Our goal was to see how void properties respond across a vast landscape of theoretical models. As you can see in the 3 configuration plot, we selected 49 distinct background cosmologists, categorized into 3 classes. First, standard random CDM, where we vary omega m and sigma 8. Second, dynamical dark energy models with time-varying evolving equation of state. Both of these classes assume the spectral index has 0 running. While third class, however, explicitly include the running models where alpha S is non-zero. Furthermore, we wanted our diagnostic to be immediately working for upcoming real-world surveys like LSST. To achieve this, we applied a strict mass cut of 10 to the 11.5 solar masses to our simulated halo and, crucially, mapped their coordinates into the redshift space. To find the void, we utilized the void finder algorithm, initially developed by Hogue and Bogerly in 2002. One of its main characteristics of this algorithm is that it merges multiple candidate pairs into a single void. It has some unique strengths on the void analysis. First, it allows us to get very precise density thresholds for the number density of particles inside the void. Second, it is very robust when using different tracers, such as galaxies or halos, even without any pre-processing. This makes it especially useful when applying the method to real observational data. The method remains powerful to show the complex structure of the voids. These are some examples of 3D void structure and outlines of voids in Abacus Summit simulations. You can see here voids have very complex and bumpy structure with varying size, morphology, and number of halos in it. Before we can safely test across different cosmologies, we must address a critical compounding variable, void size. There is several literature and the talk before that claims different initial conditions naturally produce different void sizes. You could also see them clearly here at the original samples on the left side of figure. So any direct comparison between models would be heavily biased by these size differences. To isolate the true cosmological signal, we generated size-controlled void samples. We binned the effective radii into short intervals and randomly draw an equal number of voids per interval across all of our simulated models. The result is shown on the right, a perfectly identical void size distribution across every single cosmology we tested. By using these controlled samples, we can definitely guarantee that any variation we'll see are driven purely from background cosmology, free from the secondary effects of void size. In the previous study, we numerically discovered the magnitude distribution of spin of the void, which calculated by velocities and positions of halos in it, are very well described in two-parameter generalized gamma distribution. Also, it has potential to work as effective constraint of sigma 8 and omega CDM. However, these results have a critical caveat. How could we measure void spin in real data? It is not feasible to have a catalog of galaxies with tangential velocity. To overcome this, we use 2D observational proxy, which is the maximum redshift symmetry, denoted as delta Gmax. The methodology illustrated on this slide is quite intuitive. We take the projected 2D image of void and draw a bisector through its center, like this. And we calculate the net difference of line of sight velocities, the redshift symmetry between halos on opposite side. By iteratively rotating the bisector from 0 to 180 degrees, we track how the asymmetry changes. The orientation that yields the maximum asymmetry, which you can see on the bottom right panel.
Sorry, I'm a bit lost. The void is empty, so what is spinning?
There is a lot of halo inside void still, yeah.
Dark matter halos in your simulation.
Dark matter halo and the galaxies.
I see.
Yeah.
Thank you.
So the number density of void, like compared to the other part of the universe, it has like 5% number density. And
not zero.
yeah, okay. So by iteratively rotating this bisector to, so this shows the orientation that yields the maximum symmetry, determines our projected 2D spin axis. This method makes us to effectively capture how coherently the void is rotating with only line of sight information. To quantify this redshift symmetry distribution and test if they are good proxy for cosmological parameter and void spin distribution, we fit them into generalized gamma model using two variables, a shape parameter k and a scale parameter theta. As you can see in the plot on the right side, it gives a perfect fit on Planck lambda CDM as well as 49 cosmological models. When we look at how these best fit parameters respond to different background cosmology, their behavior have obvious differences. As you can see, the shape parameter k is remarkably stable, while the scale parameter theta is highly sensitive, showing a strong systematic dependence. This stability in K provides significant mathematical advantages because it acts essentially as a universal contrast. we can securely lock K to the Planck best fit value of 6.52. By doing so, we reduce our generalized gamma model into a powerful single parameter formula. We then repeat this simplified formula to our numerical result to isolate the new best fit value of zeta for each cosmology using chi-square minimization. The plot on the right side shows that precision of fit remains high enough with single parameter. Ultimately, this transforms zeta into a direct probe for cosmological parameters capable of fitting an enormous variety of models with good precision. Next, to check how individual cosmological parameters working on scale parameter zeta, we look into the cosmological parameter zeta relation with fixed parameter. This leads to an idea that scale parameter zeta could be explained by bilinear model depending on omega matter and sigma 8. Applying that, we could make a universal non-parametric bilinear model working all across lambda CDM and WCDM models. There is one more important thing to note here. Although we tested large variety of dark energy equation of state and its time variability, the predictions still fall perfectly within 1 sigma scatter regardless of it. It provides us a robust new proof that completely immune to the uncertainties surrounding the dark energy equation of state. Now, let's look at what happened when we apply this universal valid formula to running cosmology, those where the running of spectral index alpha s is not 0. As plotted with red and blue circles, this model departs significantly from our predicted straight line. The magnitude of the departure scale directly with the absolute value of alpha s. Physically, positive alpha s leads to slow void rotation, while a negative alpha s is faster rotation. We confirm this exact same phenomenon in both redshift and real data. Because our model's universality only holds when alpha s is exactly 0, any observed deviation provides an independent test for the vanilla single-paired slow roll inflation model. Which means by simply comparing results of redshift asymmetry distribution and other cosmological constraints, we can give direct constraint on early universe initial conditions. So bringing all together, why this is so meaningful. First, it is highly practical. By probing the redshift asymmetry distribution, follow a universal bilinear generalized gamma model, we have established a robust proxy for void spin that only requires line of sight velocity information. Second, it elegantly breaks severe cosmological degeneracies. Transitional large-scale structural diagnostics like cosmic shear or redshift distortion effects are noticeably entangled with dark energy parameters. Our void asymmetry model, however, is completely independent of both W0 and WA. Finally, and most importantly, it offers us an independent testing method to constrain inflation models. It provides us clean, intermediate scale proof to resolve the tension between Lyman alpha and sigma and CMB measurement, entirely free from small scale astronomical noise. And of course, we have to think about the reason why. The results show that high sigma 8 make trend of stronger rotational amplitude. Thinking about sigma 8 is constant and reflect the amplitude of density fluctuation. Higher density fluctuation due to high sigma 8 change the strength of large-scale tidal field. As a result, the void ends up with higher rotational amplitude. Effect from the dark matter density acts in a similar way, but in different period of time. With higher dark matter density, large-scale structure form faster, which make void experience high spatial anisotropy across the evolution of universe. As a result, void rotates faster. It's more complicated in the story of running of spectral index. Look into the linear power spectrum. It looks like higher running yields higher power all across the scale, which means more compression of matter in all scale, resulting more rapid rotation of void, which is not fit to our result. But looking to the scale in typical void size, we have a totally different situation. This looks more obvious when we zoom into the shaded position, that higher running of spectral index make suppression of power in typical void scale, which makes slower evolution of universe in this scale, resulting smaller void rotation. This shows once again that void could be very essential object to test the early universe inflation models. Looking ahead, our next step will be bridge this numerical success with direct observation and deeper theory. First, we must move on from mock catalog to observation by measuring the redshift asymmetry in actual observed void. We plan to apply our framework to existing data from DESI and SESS catalog and to the larger volume next stage surveys like LSST or Euclid. Second, while our generalized gamma model perfectly describes the simulated data, it remains an empirical fit. We aim to develop physical model derived from first principles. By establishing solid theoretical foundation of void kinetics and explicitly test how its redshift asymmetry behaves at high redshift, we can fully understand void spin as a robust, independent cosmological proof. In summary, our study conclusively demonstrates that void asymmetry is good proxy for cosmological constraint as well as void spin, and the novel independent framework to test early universe inflation model. Thank you for your attention.
Thank you. Questions?
Please. I may have missed it, but I'm not sure I understand why your void is spinning coherently in the first place.
What do you mean?
Your void is, you are taking it to be spinning coherently.
Yeah.
Why?
Oh, because like according to the tidal field theory, void should appear where tidal field and I said the void candidates, like in the early universe, the major axis of spin of the void is very anti-aligned with the tidal field, like initial tidal field. So it makes the initial void candidate to spin.
The tidal field is external from external sources.
Right, initial tidal field, there is initial tidal field in the early universe.
In the dark matter?
Yeah, in the dark matter. And the void, like void appears where the anti-alignment is very high, and it makes the void spin. Yeah, it starts the void spin. Yeah.
Sorry, I didn't understand how the void is defined.
Oh, I have a full.
So density contrast smaller than something.
What do you mean?
The void is not really void, empty of halos. No, you say that there are halos inside, so it's an under density.
Yeah, it's for the number density.
About 5%.
Yeah, 5% of the.
That's what I asked him.
So we exclude like paired galaxies to meet the 5% limitation. So and we like grow a sphere. I have a slide for that. So we exclude the paired galaxies and we grow a sphere that like meets 3 galaxies around it. So it's basically like spheres that not galaxies in it, and we make number of spheres with that, and we add those spheres and we then insert the paired galaxies inside it. So this paired galaxy become galaxies inside the void. And it is how we define a void in Void Finder.
This is entirely done on simulated data until now.
Yeah, entirely in simulated data. No.
Have you looked at any real data at all? Or that's the next stage?
Yeah, that is my next job to do, and I'm looking for right now.
Interesting to see what you find.
Yeah.
Yes?
Why does the model depend only on sigma and omega matter and not even more cosmological parameters? Like I missed that. Can you explain a little bit more?
I should think more about that, but as I think is the other parameter is more affected on the non-linearism, which is right not depicts at the void. But in that kind of thinking, omega matter should be independent with void. So I have to think more about that, like why it is not changing across other cosmological parameters.
Go ahead.
So I suppose your analysis methodology also still holds independent of which sort of algorithm you use in order to find voids. So do you know maybe a different algorithm to find voids that are going to yield different results?
Yeah, I tried like 2 other ways to find void. There is like different signal, like different statistical power between the like how you define a void, but still I could get a same result, and the statistical power is highest in the void finder. So I'm using the void finder.
Did you try this Voronoi tessellation?
Yeah, I tried the byte. Yeah, Jobo byte. Yeah. Yes.
Go ahead.
So I have a question, because the voids are actually unbound, right? It's quite hard to define a spin for an unbounded structure. And you are saying that they spin because of tidal field, but we know that the tidal field itself has a lot of difficulty creating the angular momentum of like spiral galaxies, you know? It's not enough. So aren't you sort of surprised that the tidal field manages to spin these voids? And the fact that the velocity of the galaxies inside the void that you're using are so small that I'm just surprised that you can get such a good bound on the parameters, you know, and you can compete with other methods.
These are not galaxies, these are dark matter halos.
Yeah, they are dark matter halos.
The tidal field is very small, you cannot really rotate them. So it's a lot of problem using tidal field to explain like the rotation of galaxies or halos.
I mean,
you are getting that to rotate the void, which is unbound, and I don't know how you are defining the spin of an unbounded structure.
I use the halos inside the void, so it's basically angular momentum of void with using the halos inside as particles. So it should not exactly match to the like all dark matter or gases inside the void. The spin made it should be different from the spin made from the halo, but I defined
What
as
are
right.
these halo masses? Are they comparable to a galaxy, or
In this
simulation that you used?
I used the halo masses more than 11.5 solar mass, so it's quite quite big.
A galaxy mass, yeah.
Mm-hmm. Also, as I said, void, like initial condition of void is very sensitive to the tidal field. So
Do you understand the physics? Why is it more sensitive to the tidal field?
yeah,
The halo itself?
there is a like I'll tell you that there is a paper that like analytically proved that void spin is from the tidal field. So yeah.
I think that's given us enough food for thought. So let's thank the speaker now. Next speaker, Maximilian. Who's the
Yeah, please.
So I'm going to copy them just that. Emily. Thank you. Yes. full screen in the same way that you did with the other one.
Like this. And
yeah, this one. That's the moment. No.
Oh, that's the first one.
Yeah.
All right.
Yeah.
Is this the clicker here?
Yes.
I've got the microphone set up. Yeah.
That's everything, I think.
That's forward, backward, yeah. That works.
Yeah.
Oh, it's disappeared.
Oh.
Ah,
wait.
yeah.
Is that working?
There. There you go. I have to click twice to go back. All right, that's fine. We'll figure it out.
Yeah.
All right.
Okay, yeah.
All right.
We're all good. Cheers. Thank you. Sorry.
You have till quarter past 8.
Okay.
Next talks by Maximilian. Edition comes on. Well, I'll read the short title. Linear Local Galaxy Bars. The wrong title you can read for yourself.
All right, thank you very much. Hi, I'm Maximilian von Wietersheim-Kramster. I'm a postdoctoral researcher at the Institute for Computational Cosmology in Durham. And today I'll be presenting to you some of the work I've done in collaboration with Nicholas de Sorid, MSSL, Benjamin Joachimi, and Alan Hang at UCL, and now Jeffrey at King's College. All right, so what I'll be talking about today is mainly the idea that as cosmologists, we're obviously very interested in understanding the matter distribution of the universe. And we've heard about many tracers already. And my tracer of interest is galaxies. So in galaxy surveys, we're often interested in observing their positions and shapes to use as tracers of the underlying matter density. And in all of these cases, we always need to understand the galaxy-halo connection to some extent, which we also sometimes call galaxy bias. Okay, so this galaxy bias is a bit messy, and usually that's because baryons get involved. Like their human baryon analog, they like to make everything complicated. So as we know for a long time, baryons suppress the growth of structure at the power spectrum level, as we can see here, and that already affects our matter distribution by itself. There are also structure variations caused by baryons in the higher order statistics, not just at the power spectrum level. And they're already at the percent level or so at scales of about approaching tens of megaparsecs. At the same time, as you can see here in this work by Castro et al. Recently, they also can affect the halo mass function in and of itself, sort of suppressing the mass of halos that can form across various redshifts, as you can see here. Okay, so that is sort of on the growth of structure itself, but that can create sort of feedback loops as well in the galaxy-halo connection. So what you can see here is from the same work I mentioned before, you can fit the Tinker et al. Halo mass function, both with a hydro simulation and a dark matter-only simulation, and you see you get highly intentioned parameters between both of them. So you get a completely different understanding of the HMF, and that can also affect your galaxy bias. And if you then forecast that to a DR1 Euclid analysis of galaxy clusters, for example, this will consistently bias your cosmology depending on what sort of choice you make here. So that's just to illustrate that, baryons matter. So we've heard a lot about extensions of lambda CDM, and in these scales where baryons matter, also lots of extensions of lambda CDM happen to make slightly different predictions. So we've heard a lot about the neutrino mass, so that obviously also suppresses structure. So that's obviously going to be very degenerate with baryons. And then also things like extensions of gravity, like FFR, will be living in these scales mid-range that we're already able to measure with current surveys. So that paints this complicated picture, and it gets more complicated as we get more precise as we move diagonally up this plot of effective number density versus area. So up until now, so we've heard earlier about the dark energy survey, we've lived in this sort of stage 3 regime. I've done a lot of work in the past on the kilodegree survey, and we're now on the cusp of getting all this data from these stage 4 surveys, right, from LSST, Euclid, and Roman. And you can see here, they're going to achieve massive numbers of galaxies, lots and lots of area, and also resolve them with unprecedented precision and over various wavelength scales. So that's very useful, but also means all of these effects where before we were at didn't matter at large scales, now they start mattering at large scales as well, right? Okay, then the other thing is we are now entering a regime where photometric surveys in particular are going to give us lots and lots of data. So I'm mostly work now on Euclid, and in Euclid, with the VIS instrument, we're expected by DR3 to get 1.5 billion photometric galaxies, and we're only going to get 15 million NISP spectral galaxies at the same time. So that means if we want to do cutting-edge cosmology, we really want to make the most out of our photometric sample. And what you can see here is the Euclid forecasts for a DR3 release with W0, WA, CDM. And you can see here, if we do a 3 times 2-point analysis, so we combine galaxy shapes and positions and also clusters, we can achieve exquisite accuracy on most of these parameters and precision. So that would be a huge game changer because we would be essentially comparable with CMB constraining power in the late universe. So that's all very encouraging, but also very daunting for the modeling side of things. Okay, so we're going to have to use photometric data, but that has photometric redshift uncertainties. But why not take that as an opportunity to say, well, let's work in projection? So in projection means rather than modeling everything in 3D, we model things in concentric shells of projected matter, like you can see here in this work done that participated for the glass modeling. And rather than having a 3D matter distribution here, you have a 2D one, and then you have many concentric shells. So this is similar, analogous to what you would do with the CMB power spectrum, right? So that kind of projection will obviously make you lose line of sight resolution, but also has some nice properties that will help you in the modeling, and I'll go with that in detail. Okay, so we have baryons making the picture of galaxy bias complicated, and we want to do galaxy bias with photometry. What do we know about galaxy bias that is usually done? So usually, when we do galaxy bias in photometric surveys, we just assume it's linear and local and deterministic. So what that means is we assume for a given matter density field, the galaxies are sort of linear tracers that are all scales trace in an equally biased way the matter field. But we know that this isn't quite true. So we know it's not quite deterministic because, for example, here in this plot from the Dijak et al. Review, if you initialize 2 random overdensities and you let them do a random walk, so one of it, for example, would collapse beyond the critical density and another one wouldn't form a structure. So it's a stochastic process, and when you then add baryon effects on top of that, it becomes even worse. The other assumption is that it's often local. So this is called the local in-matter density distribution assumption. What that means is that you can essentially just from the matter density field alone infer the galaxy bias. But that's not quite true. We know that things like the tidal field and also environmental variables play an effect. And this is illustrated here, where essentially from M-body simulations, if you actually just permute similar density halos around your box and then measure the power spectrum again, you get a different power spectrum out, which means actually they're not independent of their local environment. So tidal effects are relevant even at these scales of 10 to the minus 1 per megaparsec. Okay, so we have this very complicated picture. What do we do? Is there even anything we can do in photometry, in the projection? So we have a wish list. We want a model to make use of photometric redshifts. So we work in spherical projection. We have all of these effects that we want to take into account that will start to matter, like stochasticity and non-locality. And we want it to be efficient and be able to run on many, many iterations of the data for modeling and inference. Okay, so the solution is we do the bias in projection, so we spherically decompose our bias field, and rather than having a fixed bias for the entire field, we still stay linear, but instead we make the bias scale dependent, so we have an L and M dependence, and I will show in a second for first principle, we also make it stochastic. So let's start with this ansatz that we have here, that we just say we're now doing linear bias that is non-local in harmonic space. What does that lead? So first things first, and maybe slightly controversial given previous talks, we assume homogeneity, and then measure get the two-point correlation function between the bias field and the matter field, so just a cross field out. And we note that this is essentially proportional to the expectation of our bias field. And if we want this to be homogeneous, this expectation needs to be independent of the given M index in our field, meaning that in expectation for a given scale, the bias needs to be independent of M, but that's only true in expectation. So since the condition is actually only on the expectation, we have the degree of freedom of actually adding an additional bias field that is stochastic, but zero in expectation. And this is how we can incorporate stochasticity into our biasing and non-locality while ensuring homogeneity of the field and, in fact, or most other properties that we're interested in. So the simplest form this can take, since in harmonic space our BLM indices are complex, is this complex Gaussian. And we can generally make this a complex Gaussian with this kind of correlation, covariance. And for details that I won't go into too much now, if you want the resulting galaxy field to be real, which you have to because it's observable, these correlations have to be zero. So you actually find that the simplest model for linear bias that allows for stochasticity and non-locality while preserving homogeneity has to be this kind of uncorrelated Gaussian with a zero mean in the complex direction, in the imaginary direction, and the sort of standard deterministic bias in the real part. What that produces as a prediction is if you then compute the power spectrum of your galaxy field, so the biased field, you get these three contributions. So you get a contribution from your deterministic bias, and then this contribution from your two stochastic biases. So what does that look like in practice? So here you can see a representation what local bias would look like in this picture, the standard one that's usually assumed in photometric surveys, and it's just flat. Non-local bias, for example, you could have a scale dependence in here. And then if you have stochastic and non-local bias, you can see the total is scale dependent, but each of its contributions also is, and you can't quite explain the full contribution with deterministic bias alone. So that's all well and good. Is that actually what's happening? Well, we've tested this in the Flamingo hydrodynamical simulations that we've run in Durham. And so they've been mentioned before, but just as a brief outline. So it's a multiple gigaparsec box with highest particle resolution at these scales to date, running hydrodynamical simulations with accurate simulations of black holes as well. So we used this for testing on used essentially boxes where we measured the galaxy bias and also taking into account all these baryon effects I mentioned earlier. So first of all, we measured the power spectrum of a modeled galaxy field and the galaxy field that's actually in Flamingo. And as these are, this model is designed to match the two-point statistics almost by construction, we find out they agree perfectly, right? So these residuals are just cosmic variants and agree perfectly well. If we then look at the one-point statistic of our harmonics, we also find, neatly, that they are Gaussian distributed broadly in every single L bin. So this assumption that I was bringing earlier that the stochasticity is, in its simplest form, Gaussian, seems to hold in the Flamingo simulations where we have full access to the formation history. Now, here is this picture from earlier again, but now measured from the actual Flamingo simulations. And you see, even at scales that are well measurable with current surveys, you start seeing a scale dependence, and you start seeing that at small scales, the stochasticity term starts taking over. So here I'm showing 3 bins at redshift 0.5. This is the bin of halo mass 10 to the 1 to 10 to the 12. This is 10 to the 12, 10 to the 13, and this is higher mass halos from 10 to the 13 and above, which would be mostly the ones relevant for lensing. And you can see the scale-dependent bias is in scales that should all be well detectable, and stochasticity is necessary to explain any of the biases we see here as well. So here's the sort of 3D plot to show you the full breadth of the parameter space, and you can see that, yeah, the scale dependence happens across all redshifts. For lower mass bins, at higher redshifts, it becomes flatter as you approach sort of more linear biasing, and at the highest mass, it also sort of plateaus out, but with a slight gradient to the left. The stochasticity also varies with redshift, and in fact, the pattern slightly changes with redshift as well. Now, here is a full sky map from Flamingo of a light cone at redshift 0.5. And if you then use this model to just take in the matter distribution from Flamingo and use the model to populate it with galaxies, you get this map. So hopefully, it doesn't look too different to you, because I think it doesn't. So I'll go back and forth a bit. And it roughly looks like a just slightly different noise realization of it. And that's by design, because it's a stochastic model. We actually draw from this random Gaussian distribution that I was mentioning earlier in the stochastic term to create a specific realization. Now, to be a bit more detailed about this, we can also zoom in. So here's a 10 degree by 10 degree cutout at redshift 5 for the lower halo mass rate. So this is the most nonlinear scales. It's low mass and low redshift. And you can see on the top is Flamingo. Here is the Bose model. And then here on the right for reference is standard linear bias, where everything's local and deterministic. One biased from a collapsed matter field. So this is just where we just count the matter from the halos. And here's from the total matter field. And visually, there is some reason that to show that these two are closer. If we look at the residuals, this becomes more apparent. You can see here the residuals between the Bose model and Flamingo are actually more consistent with noise, while if you look at these other two residuals, there appear to be more residuals with coherent large-scale structure left in the field. The same is true at higher redshift, higher mass, where scales are a bit more linear. You can see things here. And if we look at the residuals again, now the picture is less obvious, because we're now in the regime where bias is more linear and a bit more deterministic, so the model sort of reduces to standard linear bias. But you still outperform, particularly if you go directly from the matter density, which is what typically is assumed in standard analyses. To be more quantitative about this, let's measure higher order statistics of the field. So what I'm showing here is the measured angular bispectrum, in fact, the equilateral terms only, of these different fields here. So we have the true field in blue, that shows you what's in Flamingo, and then we have the various local biases in red and orange, and then there's a Bose-Mock in magenta. And what you can see here is up to a certain scale, which depending on the redshift is of the tens of megaparsecs. Yeah. They are all, the Bose model is consistent with cosmic variance and agrees well with Flamingo. And then past that, there's a bias of about 10 to the minus 1, which is coherent as we start hitting the nonlinear regime. Remember, this is still a linear model, so it will eventually fail. But it's still an order of magnitude below of the bias that you would assume in a standard local linear bias model. Note here, nothing in the model has been conditioned on the bias spectrum. The model is measured the power spectrum of the galaxy field, but knows nothing about the galaxy field's bias spectrum and is able to reproduce it down to these scales quite well. Now, we've also measured other types of higher order statistics. I won't go into too much detail, but we've also measured wavelet phase harmonics. They're essentially looking at if you measure wavelets, which are directional convolutions of different wavelet scales. So imagine it like a wave packet that you're convoluting into the matter field to see what scales they correlate with. And then you can measure their covariances and build various summary statistics. So the three ones I'm going to show here is just one that is essentially the power spectrum, one that tells you how the amplitude and the phases of a field couple, and another one that shows you how adjacent scales couple with each other, which tells you things about like filaments and sheets. So as before, at the power spectrum level, things kind of match by design, but you notice that at these at some scales, the linear model, the local models actually break down, while Bolt's doesn't. That's where the scale dependence starts hitting in. But when you look at the amplitude phase coupling, the model does much better than any standard linear bias at low redshift in these nonlinear scales. If you then look at the cross-scale mode coupling, there's still some residuals in the Bolt's model, but it outperforms by quite a bit the sort of local bias. So we have a tangible way of seeing that even in these higher order statistics, the model performs better. If we then go to the regime where I said the model reduces more to linear bias at the high redshift, high mass regime, actually the local bias starts doing better in this metric. And that is due because since we're doing a stochastic model, we're actually randomly drawing modes from the distribution, which means we erase some of that small scale correlation of the adjacent modes, and a local model, which is fully deterministic, doesn't quite do that. So for certain statistics, it might do better, even though if we look at the field level, it performed quite well. So to summarize, the Bose model, I hope I've been able to show you, is sort of a minimal biased model that incorporates stochasticity and non-locality in harmonic space. It's a closed form estimator, so you can use it analytically, and it only depends on the 2-point statistics of your field. And then obviously, if you populate a certain trace or matter field, you can then add it forward, but you can also do backward inference with it. It reproduces the bispectrum down to scales of tens of megaparsecs, and also reproduces the WPH moments without ever having seen any 3-point statistics. And then all of that we can use to then characterize these two functions as a function of redshift or conditional on other properties to produce fast and efficient non-local and stochastic galaxy bias realizations for forward modeling. And this is partially what I'm doing with Euclid, and also which could be useful for Rubin and DESI. And then in the future, we want to extend this to various feedback models and cosmologies. So as you might know, Flamingo has been run at various different assumed feedback models and very different cosmologies. So we could even condition these parameterizations on those. And of course, we can then also introduce imprints of the neutrino mass and modified gravity and other things. And I will leave it here. Thank you very much.
Thank you. If you had scale-dependent bias, then that's totally degenerate with neutrino mass imprint. So are you going to be able to convince people which one is responsible for what is observed?
Yes, so in this case, it probably is partially, since Flamingo has neutrino mass in it, it probably is partially neutrinos. But when we want to populate, say, or we want to model the galaxy bias in our simulations or in our inference, we can't really disentangle those anyway. So the way to do this is, if we think of it in the forward modeling framework with simulation-based inference, what you can do is you can make these parameters conditional on the neutrino mass. So say you calibrate this with various flamingo simulations, and then you could do an inference of the neutrino mass, and you would naturally incorporate degeneracies with also, say, the feedback parameters, right, as the well-noted baryon feedback neutrino degeneracy. Yeah.
Yes, sir.
I might have missed it, but how effective is it to apply to photometric surveillance? I mean, what is your error budget for that? Because, I mean, I understand that with redshift surveillance, that might work quite well.
So this is precisely targeted at photometric surveys, right? Because we don't, in photometric surveys, we don't have any, well, we have limited line of sight information, but that also means we typically work in projection. The thing is, when you measure, when you measure two-point correlation functions in, say, weak lensing or photometric galaxy clustering, you typically go up to scales of L of 1500. So this scale dependence you already see. You just, as you can see, but usually you're just sensitive to the high mass halos where you don't necessarily take it into account, or you assume it's all deterministic, so you don't need to worry about this. But actually it was already noted, I believe, by Will Percival and others in SDSS, that there is scale dependence, even that already detectable at the SDSS level. So stage 4 photometric surveys will definitely be able to detect it.
Yeah, but you have a huge error in the photometric redshift.
Not particularly in the sense, because in the photometric errors, they give you essentially if you have your calibration works well, you have a redshift distribution that tells you what is the 3D bulk of galaxies that you are detecting in a given shell. So in these shells, you would then be able to characterize that as well. And actually in the sort of, if you do a forward modeling sense of this, you would actually do this in discretized shells that sort of individually resolve your photometric, your redshift distributions more finely. So you could also sort of introduce some line of sight information by just doing very, very fine projections as well, and you could still harness this.
Let's thank Max for a very nice talk.
Thank you.
And, wait for 10 minutes, back at 4:30 for Marco Bruder's talk.
So if it's like, well,
It's part of my postdoctoral program. So I think my PhD is come back to the 2 years ago. I feel like working on research like simulation. I'll be here for the next
you can put it on me. I don't know where it goes.
Hello, hello. Can you hear me? I was following the chairman.
You should be able to go back and forth from there. You can also use
Oh, is there a laser?
yes, on the top of it.
So this is a laser, and this is back and forth. All right. Okay, I start again. So I was saying this is a picture of the Peak District. You can see a peak surrounded by valleys. And the second thing I wanted to say is that 2 days ago I was looking again at the web page set up by Alexia and realized that the topic of this meeting is scales very, very large. So I decided that I should broaden the scope of my talk. I can't just talk about small objects like black holes. And yeah, so I'll talk about relativistic effects on large-scale structure from largest to smaller scales. So, Alexia, can you adjust the slide because they are clearly... Okay, so this looks in phase. Yes.
Yeah?
Okay, good.
Is that going to keep working?
Let's hope so.
Okay.
Right, so basically I'll start with the question on lambda CDM. However, let me emphasize that I'm playing the part of the conservative here in the sense that I'm assuming just lambda CDM as a background. And in fact, even lambda counts very little in my talk, okay? It only is needed to work out a redshift starting from today to the past. So then I'll talk about GR vector modes, general relativity vector modes, also known as frame dragging potential from Newtonian and-body simulations, and then dig deeper into more relativistic simulations and describe a cosmic web of overdensities, voids, and filaments, and quasi-spherical collapse, and why the top path model works so well. And then I will quickly move on to looking at all the new conjectures and illustrate some work in progress. Okay, again, I don't know. For some reason, here, the slides don't move as they should.
Will that work? Yeah. Oh, is that fixed? Oh.
Does it work? Yeah, okay.
Oh, thank you.
It looks like it's working. Okay, so concordance model, lambda CDM, moving on. So we base our model in cosmology on 3 fundamental ingredients, homogeneity and anisotropy, which give us a background model. Then we use relativistic perturbations to describe large scales from the early time when we model inflation and perturbation generated in inflation up to the CMB and large scale structure on the very large scales. First order, even second order now is important, for instance, those working in non-Gaussianity. So that's the technique that we use. Also, other method also based on general relativity known as the gradient expansion or long wavelength approximation. But then when we study nonlinear structure formation, we resort to use Newtonian methods, especially n-body simulations or other approximation technique like Zeldovich or 2LPT. Okay, so on this basis, well supported by observation, the flat lambda CDM model has emerged as a standard cosmological model. Right, so in other words, when we look at the units at very, very large scales, we use a relativistic view, but then when we zoom in, we use a Newtonian approach. So then the question I'm trying to
look at is if the third assumption, the third pillar of our modeling is good enough. That's what I focus on, okay? We have more data, we look at precision cosmology where we aim at measuring everything at 1% precision, and observation and simulation cover a very large fraction of the Hubble scale. So then, in the last 10 years at least, I've been looking at this question if it is timely to bridge the gap between point 2 using relativistic perturbation theory or other methods at very, very large scales and what we do on smaller scales. And then, because of this, I will look at GR simulation with numerical relativity or other quasi-GR code where there are some approximation, or even just looking at just standard embodied Newtonian simulation, but using a GR perspective. After all, Newtonian gravity is just a leading order approximation to general relativistic gravity, and so when you can look at this from a weak field perspective, but I'll say more. All right, so I start from this GR interpretation of standard Newtonian embodied simulation. And I want to talk in particular about some effects. So let me explain this very quickly. Again, the top of the slide is not showing properly. Okay, I see it's properly shown there. Okay, so frame dragging or gravitomagnetism. So in general relativity, if a mass moves, then it generates what is called a gravitomagnetic field, similar to what happens in electromagnetism if you have a moving charge. Okay, and this is normally mostly associated with rotation, like frame dragging on neutron stars and black holes, but is not associated only with rotation. You can have a generic gravitomagnetic field, okay? So let me point out also that although this is well known, for instance, in neutron stars and black holes, this actually arises in weak field as well. And in fact, this is an effect which is measured around the Earth with satellites, okay? The frame dragging of the Earth is measured. Okay, so how we can extract this using a standard Newtonian embodied simulation. And this work first started now more than 10 years ago. And basically, the idea is this. You consider a weak field approximation in general relativity, and then the leading order is Newtonian gravity, okay? And so you recover the standard equation of Newtonian gravity, but from the zero-I Einstein's equation, it turns out that the nonlinear momentum density field sources, or the curl of it, more precisely, sources this B field, which is a gravitomagnetic potential, okay? So using this, then you can see that this at leading order can be computed from Newtonian simulations, okay? And then you can set up your calculation and compute this field as a new vector field that you extract from the simulation. It is very important to notice that this term is truly nonlinear. So although, so in other words, you see that if you are in a perturbed regime, you will neglect, because these velocity fields are first order, multiplied by delta, you will neglect it, okay? But here delta, however, is completely nonlinear. It's the one that you compute even on the smallest scales in a Newtonian simulation, okay? And so, because of this, recently we have worked with this student in particular, which visited me from Turin, using this method, using the Illustris TNG embodied simulation, just the cold dark matter part, and using a different snapshot at different redshift, and we extracted this gravitomagnetic potential. Various simulation at various scales. The three red dots are the one we actually used. And here are the results for, at the top left, the usual density field of a simulation. And the bottom is the gravitational potential, the scalar gravitational potential. But on the top right, you have the vorticity field. and which is part of the source term for this B field, and B is the module of the B field on the bottom, okay? So this can be extracted from a Newtonian simulation, and in fact, we did also this nice plot. I really like this, that where we actually plot the field line of this vector potential, okay? On the left, is a simulation box of 200 megaparsec, and the one on the right is a smaller one, and with higher resolution, okay? Okay, so actually this work was a follow-up from some work which was done a few years back with people in Durham using a code which is called Gramsci's, which is an n-body code which is built on Ramses, which is another Newtonian n-body code. But Gramsci's is a code where actually is almost full GR. Almost is just to say that there is some technical approximation which neglect some terms. But let's say basically we neglect gravitational waves, if we want to say something rough, but giving an idea, okay? Anyway, this is the result that we did at the time. And this is what I want to show you here is that although this effect is small, is really non-perturbative. So this, the thin line here are the result of second-order perturbation theory, okay? And the thick line are those from the simulation. So this is to say that in cosmology often we have this naive idea that something small you can compute perturbatively, but actually it turns out that the difference between linear perturbation prediction and the full result from the simulation is almost 2 orders of magnitude difference, okay? Right, so moving on, just to illustrate a bit, these are the plots for a smaller halo, and from left to right, we have the matter density field, the gravitomagnetic potential, and the scalar gravitational potential. And as I said, this is a smaller halo, and you see the effect is rather concentrated, and when the halo is larger, the effect is much spread out, and finally, for a very large halo, the effect, which is still not probably fully virialized, the effect is very large. All right, so now let me move on to the main part of my talk, where I really want to talk about full numerical relativity simulations in cosmology, using what is called the Einstein toolkit, which is a code which is based on a fluid assumption. So matter is treated as a pressureless dust, as we call it in GR, okay? So therefore, the limit of this analysis is that it breaks down at the first shell crossing, okay? Because the fluid approximation is no more valid at that point. However, the advantage is that we can do really full GR simulation. Also, and so just to give a bit of historical perspective, the first work was done more than 10 years ago with Eloisa Bentiveglia, and it turned out in a month, 2 papers appeared in the archive, both clearly were PRL submission. So I contacted Glenn Starkman, which was the leader of the other group, and we decided to go together on PRL. In the sense, we asked the editor to go back to back, and we succeeded. So it was a nice story. Anyway, the motivation at the time was that back reaction. So I'm using some slides for this because this back reaction issue has been mentioned recently. Basically, very shortly, back reaction and averaging and fitting problems are all problems that have been mentioned, in particular my supervisor, George Ellis, since the 80s. And the idea is simply that because general relativity is a nonlinear theory, averaging the The equation is not the same as working on the equation on the average. So in other words, there is no commutation. And so then this puts some question about how we use Robertson-Walker models. But let me really just go to the main idea. So at the time, 20 years ago, there was this idea that once dark energy came out, some people started to think, oh, maybe structure formation back reacts on the general expansion. And so while if we have omega lambda evolves the universe from an Einstein-de Sitter matter phase to a de Sitter phase, maybe we have something similar, but due to some back reaction effect. So because of this, we actually, with the full, so this back reaction in particular came out in the formalism set up by Buchert, and it is like an additional effective terms which appear in the averaged Friedman equations, okay? So then, if you do in that setup, however, you don't have a way to actually say something about this term, okay? However, if you do a full GR simulation, then you can just compute everything, including averaging in your simulation box, and then you can see what this effect is. And that's what we did. So even starting with very large initial conditions in the density field, in the peaks of the density field, we found that if you can cast these back reaction terms in an extra density parameter omega q, okay, and we found that this effect is always very, very small. It's measurable in the simulation. Okay, so you can compute it, but it's very, very small. Right, that doesn't say that the back reaction is completely solved, in my view. There are technical issues, but I am happy to discuss that if someone is interested. But I think broadly speaking, I think we settled the idea that back reaction can't really work to explain the acceleration of the universe. Right, so more recently, we resumed that type of analysis with the former student now, Robin here, on the day of her Viva. And we used the same setup, which I'm now going to illustrate a bit more detail, with this, what I call quasi-spherical collapse. In particular, we wanted to investigate if the so-called top hat model, which is a useful analytic tool at the base of the mass function in cosmology and the Press-Schechter method and other methods, is good enough in full GR. That was the goal, the main goal of the work. Okay, and so because of this, you see, the idea is the following: you want to find a possible GR effect. And so basically you are looking, we know that roughly speaking, Newtonian simulations are fine and Newtonian approximation for structure formation works. So the idea is to possibly find a very tiny effect, okay? And so using realistic simulation, you will not find the possible effect will be lost in a realistic simulation, very hard to detect. So the idea is to use a reductionist approach where we set up a very, very simple cosmic web made by peaks, voids, and filaments, which is set up by this function down here. And in particular, we assume this spatial distribution for this variable, RC, which is commonly used in gauge invariant relativistic perturbation theory. Okay? It's a curvature perturbation variable. Okay? And then from this, we set up our initial condition, and then we let evolve with the code in full nonlinearity. Okay? Let me emphasize again that this is CDM represented by dust with this fluid code, Einstein toolkit. Okay? Right, so just to give you an idea, just of this spatial distribution, that function, if you set different values of constant, when C is 1, is a tetrahedron, okay? And then large C, like in the bottom left, means you are very close to a peak, and that gives you an isosurface, which is almost spherical, okay? Conversely, if you go to small values, or even negative value, you bridge, remember these are periodic boundary conditions, then you create these bridges or filaments from one over density to the next. So that's why we use this super simplified lattice structure, let's call it, okay? So we use RC as our fundamental variable. RC in perturbation theory at first order is connected with the tree curvature of the slices. By the way, we are using a synchronous comoving gauge here. And then we set up initial condition corresponding to a growing mode in the perturbations. Like if, in other words, we set up initial conditions which are formally those of first order perturbation. You give, for those not clear about GR and specifically numerical relativity, you have two sets of initial data, the metric and the so-called extrinsic curvature, okay? These are your initial data, and so we give the metric and the extrinsic curvature formally as dictated by the growing mode at first order, okay? But you give this to the code, and the code doesn't know that that is an approximation. And if you treat everything non-linearly, and in particular, given that metric, you can compute the full three-dimensional spatial metric, so the K here is the extrinsic curvature, Kij, and K is the trace, and R3 is computed fully non-linearly, and then using the Hamiltonian constraint, you reconstruct the density field corresponding to that initial distribution in RC. So that's what we did. So this is just to show the density, isodensity hypersurfaces, at delta 0.01. And the initial conditions, by the way, are given at redshift around 300, okay? Two different points of view of this distribution. So you have a peak inside that blob, filaments, and voids outside. Okay, so this is the same density field, but from a different perspective. So the goal, as I said, was to consider the check the top path collapse model, and which is important in modeling mass distribution in cosmology. And from the GR perspective, once you reach that so-called turnaround point, that blob behaves exactly like the Oppenheimer-Tolman-Snyder collapse. So anyway, that's the picture. Basically, a top path is like a closed universe which evolves, expands, reaches a turnaround, and then collapse. And this is a plot of what happens to the density field, okay? The delta, in comparison with the linear density field, which is used as a clock. So when delta linear is 106, you are at the turnaround, and when delta linear reaches 169, you reach collapse, okay? So what we want to verify is the same, we get the same in this simulation, which is not spherical, although it becomes more spherical around the peak, okay? And, okay, I skipped these details on various quantities. We find that indeed the top path model works very, very well for the peak of this mass distribution, okay? This was a kind of surprise. I mean, in a sense, you know, if you work on this kind of thing, you will hope to find something new and that could revolutionize the field. But no, we found that the top path works perfectly well in this, even with this full GR simulation, which is non-spherical. Right, okay, and we computed some invariants like the electric and magnetic part of the Weil tensor, which were mentioned by Roger Penrose yesterday, but let me move on. So why the top path works so well then? Okay? In particular, I'm talking about the peak of the distribution. So this equation, the Reich-Shadur equation, for those that don't know it, is a general relativistic equation which governs the expansion without any assumption about symmetries. Okay? This equation, when you consider Robertson-Walker model, theta is just 3h, sigma, which is the anisotropy, the shear, and omega is the vorticity, R0 for homogeneous anisotropic case, and this equation just becomes the Friedmann equation, okay? Right, so why that top path works so well? Because if we look at the different contribution in our simulation box, from left to right, from where we have a peak, this is a round turnaround, okay? When the peak reaches the maximum expansion and then start to collapse, and this is just before collapse, okay? You can see that in this equation, by the way, we assume, by assumption, we consider just a zero irrotational dust, okay? Which is a common assumption. So then you can see that if in that case, in this equation, the only term which makes the difference between this equation and the Friedmann equation is the shear, sigma, okay? So you can see that what happens in our simulation, in our distribution, is that the shear, which is the green line, is always very negligible around the peak. And so basically the peak evolves without knowledge of the external world, as if it is a closed Robertson-Walker model, and therefore that's why the top path works so well, okay? Right, how much time do I have?
2 minutes.
2 minutes, okay, well, okay. This is progress following from that work. We want to explore the same situation, but using particles, because as I said, with the fluid description, you have to stop at the first shell crossing, okay? If we use an embodied GR code like Gramsci's, we can go beyond that, and also we can introduce some anisotropy at the peak, and so to break up even more the symmetry at the peak, okay? And this is work in progress. The one thing that I want to show is, for the moment, is the most exciting, is that what we find is that if we measure omega k in the simulation box, so we measure the average curvature in the simulation box, we find that it actually is growing. It's a small quantity, but it's actually growing. And for computational cost reason, this simulation starts again at Z300, but we stop at Z9, okay? So, but you can see that it continues to grow. So that is something to understand better and work on. Right, but let me go back from this almost Newtonian world to even smaller scales where we become very relativistic. Okay? Because the fact that this top path model works so well, naturally, in the head of a relativist, like I am, rises the question, wait a minute, if it's so much close to an Oppenheimer-Snyder, maybe we can form a black hole in this way. Okay? And so we have been working on this with that former student, and let me mention that further motivation arise from the fact that meanwhile we found that James Webb find object at Z even greater than 10, and there are supermassive black holes at that redshift. So this naturally brings up the question how they can form. Okay? The standard model supermassive black holes are through accretion but on superstars. Okay? But those are very complicated models. Okay? And the other thing I want to mention is that there are already Newtonian simulations based on self-interacting dark matter, which claim that there is black hole formation, but that is due to the self-interaction. Instead, I'm just talking about cold dark matter, but in full GR. Okay? So these are some a possible example. Again, with this Einstein toolkit, we try to see if we form an horizon. Okay? This is very, very complicated. It turns out that for the moment is or an overwhelming problem. A rough idea can be given by this picture. You see, this is 2m over r, where r is the circumferential radius. So basically, if you are above 1, possibly it means you are forming an horizon, okay? But that's a rule of thumb kind of thing. In reality, in order to find an horizon, you really have a full GR code that measure the expansion of the outgoing null direction, okay? And they should have zero divergence, and at that point you form an horizon. So we go back, because we can't find a solution with this numerical relativity code, which is too complicated, we simplify the problems even further, and we go back to good old LTB models and look at spherical models. And let me make this comment, and it's kind of funny because LTB models are very well studied, okay? But they are not, I don't find in the literature any attempt to actually evolve LTB from standard growing mode perturbations, okay? That's what we did, and in particular, we look at various peak distribution, okay? And we, in particular, concentrated on a smoothed Gaussian, like this, in such a way that at a certain radius, this is matched to a flat lambda CDM model, okay? But inside, we have an overdensity surrounded by an underdensity, okay? Which also defines a very well, the overdensity then defines a very well-defined region, which can collapse and then form a black hole in a finite time, okay? And so that's what we find. So this is the distribution, again, in this RC at the initial value, okay? And you can see that this is the density. So this is a specific example where this overdensity has a radius of 2 kiloparsec only, okay? And then we evolve, and then we find that indeed this forms an apparent horizon. So that's a possibility that we form masses in the range 10 to the 3, 10 to the 6, at z of the order even 10, okay, just through collapse of the CDM. So let me go to my conclusion, and I stop here. You can read it. Thank you. I couldn't stop myself. Questions? Joe.
It must be difficult to form a black hole in CDM. I mean, the standard simulations find an NFW like cusp, etc. And I don't think that would ever lead to black hole formation from what I've seen. How do you overcome that?
Well, from a GR perspective, there is this point to understand that. No, in Newtonian gravity, the attractor for any collapse is a pancake. Okay? But in GR, that is not always the case. So depending on the initial condition, your collapse can be a pancake, or what we call a shell crossing, which leads to what we call a weak singularity, which interpret as due to the fluid description rather than being a real singularity. Or you can have an effect where instead you go to a spindle-like singularity, which is we give this spaghettification effect. I like this counterposition of spaghetti versus pancakes, being Italian. So basically, at that point, there was one of the drawing by Roger yesterday, which pointed out the difference between Ricci curvature and Weil curvature. So this is the main difference. The spindle-like singularity is Weil dominated. So at that point, there are two things that happen. Basically, matter becomes negligible. So because you see, I agree that there are these cold matter scenario begs two questions. One is matter remaining cold even at the highest density when you form the black hole? That's one question, or if you like, you can translate that into velocity dispersion, okay? And to me, the answer to that is that this picture can only be valid not for arbitrarily small masses, but only for very large masses, because the largest is the mass, the lower is the density, and therefore the lower is the velocity dispersion, and basically you form an horizon before you reach, you break the dust, the gold assumption. And this, the other fact is that in any case, you become, there are initial conditions that lead to a Weyl-dominated kind of singularity, or collapse, let's say, and therefore the space-time deformed the matter distribution in that specific way, and matter ultimately is negligible with respect to the Weyl curvature. Essentially, the curvature is just Weyl-dominated, rather Ricci-dominated. Yeah.
If you need a singular profile, which could happen in certain types of, asymmetric collapses, but I just wonder how generic that is.
No, sure, that's the thing to investigate. So in fact, in this work in progress, we are looking not just at LTB, but also with Segres models, which have a kind of dipole. You work on that, so you know that Segres models. They contain a kind of dipole matter distribution, but essentially the monopole is dominant, and so basically we obtain the same. Of course, the question is what happens if you have something more generic than this, and that's why ultimately I would like to answer this question using a code, a full numerical relativity code where there is no symmetry. Okay, but again, recalling something that was said by Roger yesterday, the picture that I have in mind is this. So the very generic singularity in GR is the one described by Lipschitz, Kalatnikov, Belinsky, okay? Where you have this, in that case, the generic case, because you see in both LTB and Segres, basically you have a symmetry around the radial direction, right? So two shear directions are the same. So basically you have one pancake versus one cigar. Okay, so it looks like one versus the other. But if you have the three-dimensional picture, then pancakes are the exception, and the generic collapse is a Kastner face, and then so spindle is generic. So that's the picture I have in mind. Yeah.
It was a very long 2 minutes.
Thank you. Sorry.
No problem. It's just that he's running out of time. So
okay. But we were 10 minutes early anyway.
Now we're 5 minutes late. We have one last talk today, so let's make time for that.
There we go. Thank you. Thank you very much. Could you clip this onto a pocket and clip this onto your lanyard? Mia, and then I'll just get your slides working.
Hopefully this works.
Okay. Last talk by Olga on the Lyman alpha forest.
Can I just check?
Yes.
From perfect. And then if I want to point out something, it's like in the screen or I can just point out here. Perfect.
Yes.
Okay.
Yeah.
Okay. Hi everyone. So my name is Olga and I'm a PhD student at the Institute of Astronomy in Cambridge. And today I will be talking about constraining dark matter models using high redshift Lyman alpha forest data. So we know that lambda CDM has been very successful on large scales, but as we have been discussing over the past couple of days, there are still some big problems, some big questions. One of them being, what is the nature of dark matter? So here I am showing what is the range of masses that dark matter can take, you can see that it's spanning almost 40 orders of magnitudes, when in reality we even have more higher mass candidates. So I'm going to start with the most well-known candidates for CDM. These are weakly interactive massive particles, but after decades of experimental efforts at detecting them with the Large Hadron Collider, for example, no success has been achieved so far. If we go between KEV and MEV regime, we go into light dark matter or warm dark matter, whose main effect is to suppress a structure at a few megaparsec scales or so. And then below the KEV, we go into the ultralight dark matter regime, where perhaps the most promising candidate is the action. So the QCD action was initially proposed to solve the strong CP problem of QCD, but then it was later realized that coherent oscillations of the action field exactly mimic the behavior of pressureless non-relativistic CDM, which is why it is such a compelling cold dark matter candidate. We also have more generic action-like particles that extend, as you can see, the lower mass end, and these are not necessarily tied to QCD. These, for example, are predicted in string theory models or other high-energy extensions of the standard model. And so in this, and another thing that I wanted to say is that there is also a strong experimental efforts at detecting the action, which, for example, ADMX, and the UK is involved in some of these with next-generation projects as well, such as, for example, ALPHA. So in this presentation, I will be talking mainly about two of these, warm dark matter and these action-like particles. So for action-like particles, I already set the context for them. What is important about the action is the energy scale at which they are generated. So this scale is FA, and the reason why it is important is because whether this symmetry breaking scale that establishes the action occurs before or after inflation will have very important cosmological consequences. So if we look at action-like particles, these are more generic, as I was saying, not necessarily tied to QCD. So MA and FA, MA is the action mass, are not necessarily bound together. We're looking at post-inflationary actions. These are the models that I'm interested in. And in this case, this energy scale occurs after inflation, so it's lower than the inflationary scale. And the reason why it's interesting to look at this is because the misalignment angle, in this case, varies from uncorrelated patches of the sky. So what this means is that nowadays in my comoving horizon, I see very different values of theta ini. This is the vacuum realignment angle. And what this means is that I can average over all these possible values, and I get an effective value of pi squared over 3. And the main consequence of this is that these random fluctuations in theta from patch to patch will result in isocurvature perturbations, because the action density scales with theta. So these random fluctuations, or white noise, which is what isocurvature perturbations really are inherited in our structure growth. And now going to the left-hand side to the warm dark matter models that I look at, the main characteristic is that these candidates have a non-negligible velocity dispersion when they decouple compared to the basic definition of CDM, which is the opposite. And what this is going to cause is that they are going to free stream damping structure formation below the free streaming scale. So you can think of this as similar to the Jeans length for a collisional fluid. And for thermal relics, these free streaming scales inversely with a mass. And it's also interesting to look at models where a fraction of dark matter is allowed to be warm. So these are cold plus warm dark matter models. And the reason why it's interesting is because if we think of the simplest extension of the standard model, so if we think of neutrinos to being heavier, these are also called sterile neutrinos. And within some production mechanisms of these sterile neutrinos, the velocity distribution of these particles will have two components, a warm and a cold one, fitting this mixed dark matter model description. So now I'm going to talk a little bit what is the imprint that they leave, these isocurvature perturbations and this free streaming damping on a structure formation. And in order to do so, I'm going to refer to a slide through a cosmological box of size 20 megaparsec that I used on my work. These are hydrodynamical simulations. And you can see the cosmic wave for cold dark matter with higher density regions shown in brighter and lower density regions shown in darker colors. And we can also do the same thing. We can run the simulation for these two cosmologies that interest us. So for action-like particles on the left and for warm dark matter on the right. And you can see this enhancement of clustering from the isocurvature perturbations is very noticeable, whereas the smoothing of this clustering is very observable for the warm dark matter due to this free streaming effect. And in cosmology, when we want to quantify this amount of clustering over different scales, what we use is the matter-power spectrum. So this is the matter-power spectrum, or better said, k cubed times the power spectrum. So this is the variance per natural log in k. And this is the prediction that we have for CDM. And for the isochorometer perturbations seeded by action-like particles that I just mentioned, this is how the power spectrum looks like. So if we look at the form of the power spectrum, if we fix the spectral index and iso to be 4, this P iso, so the power spectrum of the isochorometer component, is just flat. That's why in this plot it scales as k cubed. And this is the power spectrum predicted not only for action-like particles, but also for models of primordial black holes, which have also been mentioned around in the meeting. And so for action-like particles, what really emphasizes about this model is what is the amplitude of this component. And this depends on k oscillation. This is the co-moving size of the horizon when the action field starts oscillating. And I will just briefly mention this because the way that we parameterize this model for our analysis is using this parameter f iso, which is just the ratio between the amplitude of the isochorometer component to that of the adiabatic component at some pivot scale, large scales. And now let's move towards this other warm dark matter model. So here I'm showing the cutoff from the free streaming of the warm dark matter thermal relic. And here you can see the numbers. So for a 5.5 keV model, we can also look what is the impact of this mixed dark matter model. So now you can see that the suppression, we have a 2-parameter model now. So the scale at which we depart from CDM depends on the mass of the candidate, whereas the amplitude of the plateau, because we still have this cold dark matter component, is set by the fraction of warm dark matter. And here I'm just showing a variety of models, so you can see this degeneracy between these two parameters. For instance, if I allow 20% of my dark matter to be warm, or if I allow 30% of my dark matter to be warm. And this just shows the 2 sigma regions of allow model that I found in my work, from above for isochorometer perturbations, and from below for mixed dark matter models. But we cannot observe dark matter, so what we can use is something that we can see, which is gas. And so here I'm showing again these slices, these 2-dimensional slices for dark matter on the left. We have seen this before. And on the left-hand side for the projected gas density field. And looking at this gas is very interesting because most of this gas is made up of neutral hydrogen, and we're particularly interested in the neutral hydrogen that lives in these voids and filaments. These are underdense regions, so we are looking at overdensities of the order of 1, and these are the ones that really gives rise to the Lyman alpha forest. This is our protagonist. This is the main astrophysical proof that we use to constrain these dark matter models. And really what we observe is the transmitted flux from quasar spectra, and we translate this into a measurement of the optical depth. But our forest, the absorption features in the forest, that is the lines, will be broadened due to thermal motions of the atoms within the cloud that give rise to the forest. So this optical depth quantity not only depends on the gas density, as I was saying, but also on the temperature of the gas, and it will also be distorted by peculiar velocity of the gas. So you can see that actually this is a nonlinear mapping of the density field. And to model these complex gas physics that are going on, we need to use hydrodynamical simulations. So these hydrodynamical simulations come from the Sherwood relic suit. And the idea to use these simulations is to simulate the IgM before and after ionization to create flux distribution along the line of sight. So if we think of a cosmological box size and I draw a skewer, I can reconstruct the flux distribution here. And you can see how this flux distribution looks for an F-iso. So this is an isochorometer cosmology versus a warm dark matter cosmology. And you can see that this enhancement of clustering is just emphasized with these sharper features that we see now are being smoothed out or broadened by the warm dark matter component, with CDM sitting at the middle. And this is what is really compared against the Lyman alpha forest spectra. So this would be this region of lines that we see on an example of quasar, a redshift around 3.6 or so. And as I was saying before, these are my cosmological parameters, but I also need to account for my astrophysics of the gas. And the astrophysics are very straightforward. These are just the cooling and the heating of the gas. And these are going to depend mainly on the heating history. So I parameterize this with U0 parameter. This is just an integral of the heating history and depends on the redshift of reionization. As I was saying, it also depends on thermal broadening. So I parameterize it through the temperature at mean density. This is my T0 parameter. And I also need to calibrate my simulations such that the mean flux matches that one found from observations. This is what I mean by mean IgM transmission. And we have simulations that account for these variations of models, and once we have that, we need to characterize these fluctuations in the flux that I was showing before. And to no surprise, we do this using the power spectrum. So now what I'm showing here is the dimensionless flux power spectrum. So this is the variance once again. So what I'm doing is just cross-correlating the flux fluctuations along the line of sight. And here I'm just going to present the data that I use. So I use quasar data from highest and UVC spectrographs, and I use flux power spectrum measurements at these redshift pins, 4.2, 4.6, and 5.0. And here in solid lines, I am showing how the fit for one of my cosmological models, CDM, looks like. And here now, if I take the mass of dark matter to be 3 kilo-electron-volts, this is how the fit looks like. And you can clearly see these free streaming effects coming from the largest caving, so the smallest scales, that comes increasingly when I move towards higher redshifts. And maybe the main point to highlight from this data is the fact that we are able to reach these very small, very high cavings or small scales, because these are really the ones that are picking the warm dark matter signal or the isocurvature signal. And here I'm just showing in vertical lines what is the maximum cut by well-known surveys and telescopes, just as a comparison. So what we do next is that we run a Bayesian inference analysis, and to calculate the likelihood at each point in the parameter space, we want to optimize this. We don't want to run simulations for each point. That's not efficient at all. So we use a neural network emulator. And I'm just going to pass now to the results. So just as a reminder, what I'm looking here are the matter power spectrum constraints at redshift 0 for my mixed dark matter models first. So this is the shaded orange regime. And when I run this Bayesian inference analysis, I use thermal priors. This means priors on these T-node parameters. This is the temperature admin density, as I was saying, from completely independent measurements that we have from Gatewat in 2020 and 2022. And this is the main result of this paper. So this is the 2D posterior in the fraction and on the inverse of the mass plane. And you can see this degeneracy between these two parameters, which is kind of what we expected for the 1 and the 2 sigma contours. So if I move along this axis, because this is quoting the inverse of the mass, I am essentially looking at lighter thermal relics. And these lighter thermal relics are allowed with decreasing fraction. If, on the other hand, I move in this direction, I am looking at heavier thermal relics that are allowed with a higher fraction, recovering CDM at the origin. And we can also look at what happens if I now fix my mass spin, and I look at the 2 sigma constraints on the fraction. So this is what this plot is emphasizing. And so for a thermal relic of 1 kilo-electron-volt, this model is still consistent with the data just as much as CDM if the fraction is less than 20% within 2 sigma. And so on, we can play this game for the other mass beams as well. And here I'm also emphasizing what occurs if I now reduce the amount of information on these small scales. So this is this K-max analysis. And the reason why looking at this is interesting is because we can then compare it with previous results, used, for example, with Mike and Hayes data, when I fix my mass beams for different models. So we can see that this sensitivity is really coming from these higher K-beams, but also from the statistical gain of higher number of quasars that we have with this data compared with this previous data. And now looking into the other second set of results. So these are my isocurvature perturbations constrained, seeded by action-like particles. So this is this blue shaded region above CDM. What I did is that I ran a Bayesian inference analysis where the thermal priors that I used were a bit different. I essentially informed the combination of my parameters that constrain the reionization history and the thermal history from the electron optical depth, from the Planck measurements of the electron optical depth. This is tau CMB. And once I run my pipeline, what I can do is look at the posterior in FISO. This is the 1D marginal posterior in FISO. And I can see that my blue analysis is actually finding a hint of a detection at 0.006. So this is quite interesting. Remember that this signal is coming from these small scales or higher K-beams. And what this is suggesting is that this default analysis with tau CMB prior is excluding CDM at 3.6 sigma. It's also interesting to compare this FISO limit, which, just as a reminder, is the amplitude of this isocurvature component and adiabatic component at some pivot scale, back to the action mass. And also to the energy scale at which this symmetry is spontaneously broken, and therefore the action is established. And what we find is that the action mass is of the order of 10 to the 18 electron volt for my default analysis. And for the default analysis as well, this energy scale is of the order of 10 to the 15 giga-electron volt. And as I was saying before, we need to take this detection carefully, just because, as I was saying, the small scales of the data that I just presented to you are affected by systematics, and one of them is the instrumental noise. So what we consider is adding more noise to the data, and this is what we call a conservative noise analysis. So what we would expect is now that FISO signal weakens. So this is essentially what happened. We can see that now the constraints on FISO, we actually only get an upper bound of around 0.0084. And we can then do the same thing to translate these constraints on FISO back to the action mass and back to the energy scale of inflation. So these are the main points of, that I wanted to highlight from these results. So just to summarize, I have been looking at 2 different types of dark matter models that explore completely different mass regimes, but that can be equally well constrained by the Lima alpha forest. One of them enhances the power. These are isochorbital perturbations seeded by action-like particles, and the other one that suppress the power at similar scales. And then what I do is that I use high-resolution data, as I was saying, from the Lyman alpha forest, and I compare this data with flux power spectrum measurements from hydrodynamical simulations. And the main result, as I was saying, is that we find this hint of a detection that weakens when I increase the level of noise at small scales. But also, interestingly, different dark matter models, as I increase the mass bin with increasing fraction, are also consistent with the data at the same level as CDM. So in the future, we would like to even scrutinize these nodes at small scales, but at the same time, when we get more data, when we get Lima alpha forest from even higher number of quasars, we will be able also to reduce the errors. So it will be interesting to look this from the perspective of future surveys, and it will also be interesting to see what are the constraints that we get, for example, with observations from JWST future. So now, I think someone pointed out this earlier, but we have candidates at very high redshifts now. So someone in principle could find the constraints from the UV luminosity function also for these models. So this is the end. Thank you. Yeah.
If one considers actions, they don't necessarily have to lead to isochorbital perturbation.
That's right.
If the Pechequin symmetry breaks after inflation, for example, or if they are heavy during inflation.
Well, it depends on the model that you looked at. For the models that we are looking at, we are assuming that the random fluctuations in theta, like the rho A, that is the action density, scales with theta. That is exactly the constraint that gives us these random fluctuations in the matter power spectrum.
But if you break the symmetry after the end of inflation, you don't have any superhorizon perturbation from this.
You don't have, sorry?
Superhorizon perturbation.
Why not?
Because it's after the end of inflation.
But so, if the symmetry is broken after the end of inflation, you are going to end up, like your moving horizon after inflation keeps on growing, right? So you are going to see theta fluctuation from all these patches. If your symmetry breaking, of course, pre-inflation, each of these uncorrelated patches are going to continue growing into your eventually observable universe. So your observable universe will only see one value of theta. So in that sense, you will have homogeneous theta, and you wouldn't observe isochorbital perturbations. That's the main difference between the 2 models.
Okay, we'll discuss it.
Okay.
It's not yet.
Okay.
The sterile neutrinos that you mentioned, I'm not sure how relevant this is to the cosmology side of it, but I remember reading that on the particle physics side of it, the neutrinos were the main candidates for differences in, I think it was spin coupling between comparing the electron spin and muon spin, and the measurements that were done at, I want to say Fermi-Lab, but I can't remember. But they were adding constraints onto what the masses of the sterile neutrinos could be, and when they went to search for detection, they kept, like with proton decay, they kept extending the constraint. Is it relevant at all?
No, it is relevant. I mean, the first part of what you said, I'm not as familiar with these measurements, but what I am familiar with is...
Those measurements refer to 0.1 eV scale, not KeV scale. There's
But,
no evidence for KeV mass sterile neutrinos from anything in particle physics.
But it is true, however, that for these models that I was saying, the ones that at least are relevant to fit the description that I was saying, it is predicted that these sterile neutrinos will come into a family, so you can have a higher one in the giga-electron volt scale, so that's why this would be a CDM candidate, and one in the KeV scale, which would be a 1 candidate.
There was a claim for a 7 keV mass
that's right.
from this putative X-ray line from clusters, but that has been disputed, and currently status is in doubt. So neither astrophysically nor particle physics supports the idea of a sterile neutrino at the moment. But this is, of course, a completely independent way of...
Exactly.
there are no further questions, thanks again, Olga. So if it is 10 to the 15 GeV, that means inflation scale has to be lower than that.
It has to be higher than that.
Sorry, higher than that. Because
That's right. That's right.
So that's, okay, you've got a little room.